This page provides an overview of the Llama 3 herd of models, a new set of foundation models developed by the AI team at Meta. These models support multilinguality, coding, reasoning, and tool usage, with the largest model featuring 405 billion parameters and a context window of up to 128,000 tokens. The paper details the extensive empirical evaluation of Llama 3, its competitive performance with leading models like GPT-4, and the integration of image, video, and speech capabilities, although these multimodal models are still under development and not broadly released. Page 2 of the research paper provides a comprehensive overview of the Llama 3 series of multilingual language models, detailing their configurations, performance, and the methodologies employed in their development. The page begins with a tabular summary, Table 1, of the Llama 3 models, including their parameter sizes, 8B, 70B, and 405B, and release dates, highlighting that all results discussed in the paper pertain to the Llama 3.1 models. The authors emphasize the adherence to scaling laws for foundation models, noting that their flagship model, Llama 3.1405B, is approximately compute optimal for their training budget. Interestingly, they also trained smaller models beyond compute optimal durations, resulting in superior performance at the same inference budget. This approach leverages the flagship model to enhance the quality of smaller models during post-training. To manage complexity, the authors opt for a standard dense transformer architecture with minor adaptations, prioritizing training stability over more complex architectures like mixture of experts models. They employ a straightforward post-training procedure involving supervised fine-tuning, SFT, rejection sampling, RS, and direct preference optimization, DPO, eschewing more complex and less stable reinforcement learning algorithms. The Llama 3 series comprises 3 multilingual models with 8B, 70B, and 405B parameters. The authors evaluate these models on a wide array of benchmark datasets covering diverse language understanding tasks. Human evaluations further compare Llama 3 with competing models, revealing that the flagship model performs comparably to leading models like GPT-4 across various tasks and approaches state-of-the-art performance. The smaller Llama 3 models outperform other models with similar parameter counts, offering a better balance between helpfulness and harmlessness compared to their predecessor. The paper announces the public release of all 3 Llama 3 models under an updated Llama 3 community license, including pre-trained and post-trained versions of the 405B parameter model and a new version of the Llama Guard model for input and output safety. The authors express hope that this open release will drive innovation in the research community and accelerate the responsible development of artificial general intelligence, AGI. Additionally, the authors mention the development of multimodal extensions to the Llama 3 models, which will enable capabilities in image recognition, video recognition, and speech understanding. These multimodal models are still under active development and not yet ready for release. The paper also presents initial experimental results with these multimodal models, indicating ongoing progress in this area. In summary, this page outlines the Llama 3 model's configurations, performance evaluations, and the methodologies used in their development, while also highlighting the public release and future directions involving multimodal capabilities. Performance benchmark. The table titled, Performance of Fine-Tuned Llama 3 Models on Key Benchmark Evaluations, compares various versions of the Llama 3 model, 8B, 70B, and 405B parameters, against competing models such as GPT 3.5 Turbo, GPT-4, and others. The benchmarks cover a wide range of tasks, including general language understanding, general MMLU, few-shot and zero-shot learning, MMLU, MMLU Pro, code generation, code human eval, MBPP eval plus, mathematical reasoning, Math GSM 8K, math, and more specialized tasks like tool use, BFCL, and long context understanding, zero scrolls, quality. Key points from the table include, Llama 3 models generally perform competitively across various benchmarks. The 405B parameter version of Llama 3 often achieves the highest scores, particularly in complex reasoning and mathematical tasks. The table uses boldface to highlight the best performing model in each category, indicating that Llama 3 models frequently outperform their counterparts. General overview. Model architecture. The architecture of Llama 3 is illustrated in Figure 1, not provided on this page. The development process is divided into two main stages. 1. Language model pre-training. The pre-training involves converting a large, multilingual text corpus into discrete tokens and training the model to predict the next token. The pre-training is conducted on a massive scale, with the 405B parameter model trained on 15.6 trillion tokens using an 8K token context window. A continued pre-training stage extends the context window to 128K tokens, enhancing the model's ability to understand and generate long-form content. 2. Language model post-training. This stage aligns the pre-trained model with human feedback through supervised fine-tuning, SFT, and direct preference optimization, DPO. New capabilities, such as tool use, coding, and reasoning, are integrated during this stage. Safety mitigations are also incorporated to ensure the model behaves as expected in various scenarios. The resulting Llama 3 models exhibit a rich set of capabilities, including multilingual question answering, high-quality code generation, complex reasoning, and zero-shot tool use. Multimodal capabilities. The paper also explores adding image, video, and speech capabilities to Llama 3 using a compositional approach. This involves three additional stages. 1. Multimodal encoder pre-training. Separate encoders for images and speech are trained on large datasets. The image encoder learns the relationship between visual content and its natural language description. The speech encoder is trained similarly, although specific details are not provided on this page. Conclusion. This page provides a detailed snapshot of the Llama 3 model's performance and development process. The benchmarks demonstrate its competitive edge, while the architectural overview highlights the extensive pre-training and post-training efforts that contribute to its advanced capabilities. The exploration of multimodal capabilities suggests ongoing efforts to expand the model's utility beyond text, making it a versatile tool in various AI applications. Figure 1 is referenced, illustrating the overall architecture and training process of Llama 3. The model employs a self-supervised approach, masking parts of speech inputs and reconstructing them using a discrete token representation. This method enables the model to learn the structure of speech signals. The text refers readers to sections 7 and 8 for more details on the image and speech encoders, respectively. Vision adapter training. The vision adapter integrates a pre-trained image encoder into the language model using cross-attention layers. These layers feed image encoder representations into the language model, aligning image and language representations. The adapter is trained on text-image pairs, updating the image encoder's parameters but not the language model's parameters. Additionally, a video adapter is trained on top of the image adapter using paired video-text data, allowing the model to aggregate information across frames. Section 7 provides further details on this process. Speech adapter training. The speech adapter integrates the speech encoder into the model, converting speech encodings into token representations compatible with the fine-tuned language model. The adapter and encoder parameters are jointly updated during a supervised fine-tuning stage to enhance speech understanding. The language model parameters remain unchanged during this training. A text-to-speech system is also integrated, with more details available in Section 8. The page notes that the multimodal experiments have resulted in models capable of recognizing image and video content and supporting speech interaction. However, these models are still under development and not yet ready for release. Pre-training. This section outlines the components involved in language model pre-training, including the curation and filtering of a large-scale training corpus, the development of model architecture and scaling laws, techniques for efficient large-scale pre-training, and the creation of a pre-training recipe. Pre-training data. The dataset for pre-training is sourced from various data sources containing knowledge up to the end of 2023. Several deduplication methods and data cleaning mechanisms are applied to ensure high-quality tokens. Domains with large amounts of personally identifiable information, (P), and known adult content are removed. Web data curation. This subsection describes the cleaning process for web data. Filters are implemented to remove data from websites likely to contain unsafe content or high volumes of P. Domains ranked as harmful according to meta safety standards and those known to contain adult content are also excluded. In summary, this page provides a comprehensive overview of the Llama 3 model's architecture and training methodologies, emphasizing the integration of vision and speech adapters, the pre-training process, and the rigorous data curation methods employed to ensure the model's safety and quality. Text extraction and cleaning. The authors describe a custom parser designed to extract high-quality, diverse text from non-truncated web documents. This parser is optimized for precision in removing boilerplate content while maximizing content recall. Human evaluations indicate that this custom parser outperforms popular third-party HTML parsers. Special attention is given to preserving the structure of mathematical and code content, including maintaining the "alt" attribute text for images, which often contains mathematical content. Experimental evaluations reveal that Markdown negatively impacts model performance, leading to the removal of all Markdown markers. Deduplication. The deduplication process is multifaceted, involving URL, document, and line-level deduplication. URL-level deduplication ensures only the most recent version of pages corresponding to each URL is retained. Document-level deduplication employs global min-hash, Broder, 1997, to remove near-duplicate documents. Line-level deduplication follows an aggressive approach similar to CCNet, Wenzek et al., 2019, removing lines that appear more than 6 times in each 30M document bucket. Despite some high-quality text being removed, empirical evaluations show significant improvements. Heuristic filtering. Heuristic methods are developed to eliminate low-quality documents, outliers, and documents with excessive repetitions. Examples include using duplicated NGRAM coverage ratio, Ray et al., 2021, to filter out repeated content like logging or error messages. Counting dirty words, Raffle et al., 2020, to filter out adult websites not covered by domain block lists. Applying token distribution Kullback-Leibler divergence to filter documents with excessive outlier tokens compared to the training corpus distribution. Model-based quality filtering. Various model-based quality classifiers are experimented with to select high-quality tokens. These include fast classifiers like fast text, Julin et al., 2017, and more compute-intensive Roberta-based classifiers, Liu et al., 2019a. A quality classifier based on Llama 2 is trained using a set of cleaned web documents, with quality scores generated by Distill Roberta, San et al., 2019, for efficiency. The efficacy of different quality filtering configurations is experimentally evaluated. Code and reasoning data. Domain-specific pipelines are built to extract code and math-relevant web pages, using distilled Roberta models trained on web data annotated by Llama 2. Prompt tuning targets web pages containing math deduction, reasoning in STEM areas, and code interleaved with natural language. These pipelines implement domain-specific HTML extraction, customized text features, and heuristics for filtering. Multilingual data. The multilingual text processing pipeline includes a fast text-based language identification model categorizing documents into 176 languages. Document-level and line-level deduplication within data for each language. Filters to remove data from websites likely to contain PE or unsafe content. This page builds upon previous sections by detailing the specific methodologies and experimental evaluations used to ensure the quality and diversity of the text data, addressing limitations and assumptions inherent in web data processing, and outlining future work directions in refining these processes. Data preprocessing and quality control. The authors emphasize the importance of filtering low-quality documents using language-specific heuristics and model-based filters. A multilingual Llama 2-based classifier is utilized to rank the quality of multilingual documents, ensuring high-quality content is prioritized. The balance of multilingual tokens in pre-training is experimentally determined to optimize performance across both English and multilingual benchmarks. Determining the data mix. The section outlines the critical process of determining the proportion of different data sources in the pre-training data mix. Two main tools are highlighted. 1. Knowledge classification. A classifier is developed to categorize web data types, allowing for the downsampling of overrepresented categories such as arts and entertainment. 2. Scaling laws for data mix. Scaling law experiments are conducted by training small models on various data mixes to predict the performance of larger models. This iterative process helps in selecting an optimal data mix candidate, which is then used to train a larger model and evaluate its performance on key benchmarks. The final data mix comprises approximately 50% general knowledge tokens, 25% mathematical and reasoning tokens, 17% code tokens, and 8% multilingual tokens. Annealing data. Annealing, a technique involving the gradual reduction of the learning rate, is applied to small amounts of high-quality code and mathematical data. This process, inspired by Lee et al. 2024b, aims to boost the performance of pre-trained models on key benchmarks without including training sets from commonly used benchmarks. This approach assesses the true few-shot learning capabilities and out-of-domain generalization of Llama 3. Empirical results show significant performance improvements on the GSM-8K and math validation sets for the Llama 3.8b model, but negligible improvements for the 405b model, indicating the latter's strong in-context learning and reasoning capabilities. Using annealing to assess data quality. Annealing is also used to evaluate the value of small domain-specific datasets. By annealing the learning rate of a 50% trained Llama 3.8b model on 40b tokens, with a 30% weight assigned to the new dataset, the authors find this method more efficient than scaling law experiments for small datasets. Model architecture. Llama 3 employs a standard dense transformer architecture, similar to its predecessors Llama and Llama 2. The performance gains are attributed to improvements in data quality, diversity, and increased training scale rather than significant architectural changes. However, two minor modifications are noted. 1. Grouped Query Attention, GQA, implemented with 8 key-value heads to enhance inference speed and reduce key-value cache size during decoding. 2. Attention masking. Prevents self-attention between different documents within the same sequence, which is particularly beneficial during continued pre-training on very long sequences. Conclusion. This page provides a comprehensive overview of the strategies and methodologies used to enhance the Llama 3 model, focusing on data quality, data mix optimization, annealing techniques, and minor architectural adjustments. The detailed empirical results and methodological rigor underscore the model's robust performance and generalization capabilities. Key hyperparameters. Table 3 summarizes the critical hyperparameters for the Llama 3 models. Layers. 32, 80, and 126 for the 8B, 70B, and 405B models, respectively. Model dimension. 4096, 8192, and 16384. FFN, feed-forward network, dimension. 6144, 12288, and 20480. Attention heads. 32, 64, and 128. Key value heads. 8 for all models. Peak learning rate. Ranges from 3 times 10^4 to 8 times 10^5. Activation function. SWI glue. Vocabulary size. 128,000 tokens. Positional embeddings. Rope with a base frequency of 500,000. Tokenizer improvements. The Llama 3 models utilize a vocabulary of 128K tokens, combining 100K tokens from the TikToken tokenizer with an additional 28K tokens to better support non-English languages. This new tokenizer improves compression rates on English data from 3.17 to 3.94 characters per token, allowing the model to process more text with the same computational resources. The inclusion of non-English tokens enhances both compression ratios and downstream performance without negatively impacting English tokenization. Positional embeddings. The rope, rotary position embedding, base frequency is increased to 500,000, supporting longer context lengths up to 32,768, as demonstrated by Xiong et al. 2023. Model architecture. The Llama 3405B model features 126 layers, a token representation dimension of 16,384, and 128 attention heads. This architecture is deemed compute optimal based on scaling laws for the given training budget of 3.8 times 10^25 flops. Scaling laws. The paper discusses the development of scaling laws to determine the optimal model size for the flagship model within the pre-training compute budget. The challenges addressed include 1. Existing scaling laws typically predict next token prediction loss rather than specific benchmark performance. 2. Scaling laws can be noisy and unreliable due to being based on small compute budget pre-training runs. Methodology. A two-stage methodology is implemented. 1. Establish a correlation between the compute optimal model's negative log likelihood on downstream tasks and the training flops. 2. Correlate the negative log likelihood on downstream tasks with task accuracy, leveraging both scaling law models and older models trained with higher compute flops, specifically using the Llama 2 family of models. This approach allows for the prediction of downstream task performance given a specific number of training flops for compute optimal models. A similar method is used to select the pre-training data mix. Scaling law experiments. The experiments involve pre-training models with compute budgets ranging from 6 times 10^18 flops to 10^22 flops. Models range in size from 40M to 16B parameters, with a subset of model sizes at each compute budget. A cosine learning rate schedule with a linear warm-up for 2000 training steps is used, with peak learning rates between 2 times 10^4 and 4 times 10^4. The cosine decay is set to 0.1 of the peak value, and weight decay is set to 0.1 times the learning rate at each step. Batch sizes range from 250K to 4M. Conclusion. This page provides a comprehensive overview of the hyperparameters, tokenizer improvements, and scaling laws methodology for the Llama 3 models, highlighting the technical rigor and innovations in model architecture and training processes. Scaling laws and compute optimal models. The page begins by introducing the concept of isoflops curves, depicted in Figure 2. These curves represent the relationship between the compute budget, measured in flops, and the validation loss, which is the negative log likelihood on a held-out validation set. The loss values are approximated using a second-degree polynomial, and the minima of these parabolas are identified as the compute optimal models for the corresponding compute budgets. The researchers then use these compute optimal models to predict the optimal number of training tokens for a given compute budget. They assume a power law relationship between the compute budget, C, and the optimal number of training tokens, n(C), expressed as n(C) equals a C beta, where A and beta are parameters fitted from the data in Figure 2. The fitted values are beta equals 0.53 and A equals 0.29, as shown in Figure 3. This scaling law is extrapolated to predict that training a 402 billion parameter model would require 16.55 trillion tokens. Observations and decisions. An important observation is that the isoflops curves become flatter around the minimum as the compute budget increases. This indicates that the performance of the flagship model is relatively robust to small changes in the trade-off between model size and the number of training tokens. Based on this observation, the researchers decided to train a flagship model with 405 billion parameters. Predicting downstream performance. The page also discusses the prediction of the flagship Llama 3 model's performance on downstream tasks. The researchers use the compute optimal models to forecast performance on benchmark datasets. They first establish a linear correlation between the normalized negative log likelihood of the correct answer in the benchmark and the training flops. They then establish a sigmoidal relationship between log likelihood and accuracy using both the scaling law models and Llama 2 models. The results, shown in Figure 4, demonstrate that this two-step scaling law prediction is quite accurate, only slightly underestimating the final performance of the Llama 3 model. Infrastructure, scaling, and efficiency. The final section introduces the infrastructure and optimizations that enabled the large-scale pre-training of the Llama 3 model. The Llama 1 and 2 models were trained on Meta's AI Research Supercluster, but as the scale increased, the training for Llama 3 was migrated to Meta's production clusters. This migration and the associated optimizations are discussed in detail in the subsequent sections. Conclusion. This page effectively combines theoretical scaling laws with practical infrastructure considerations to present a comprehensive approach to training large-scale language models. The use of isoflops curves and power law relationships provides a robust framework for predicting optimal training configurations, while the infrastructure optimizations ensure efficient execution at scale. The findings and methodologies discussed here are crucial for advancing the state-of-the-art in large-scale model training. Scaling law models and performance prediction. The page begins with a discussion on the scaling law forecast for the ARC challenge. Two graphs are presented in Figure 4.1. The left graph illustrates the normalized negative log likelihood, NLL, of the correct answer on the ARC challenge benchmark as a function of pre-training flops, floating point operations per second. 2. The right graph shows the ARC challenge benchmark accuracy as a function of the normalized NLL of the correct answer. These visualizations are crucial for predicting model performance on the ARC challenge benchmark before the commencement of pre-training, providing a valuable tool for optimizing training strategies. Compute infrastructure. The Llama 3405B model is trained using up to 16,000 H100 GPUs, each operating at 700 WTDP with 80 GB HBM3 memory, on Meta's Grand Teton AI server platform. Each server is equipped with 8 GPUs and 2 CPUs, interconnected via NVLink. Training jobs are managed by MAST, Meta's global scaled training scheduler, ensuring efficient resource allocation and job scheduling. Storage system. The storage infrastructure leverages Tectonic, Meta's distributed file system, to create a robust storage fabric. This system provides 240 petabytes of storage across 7,500 servers equipped with SSDs, supporting a sustainable throughput of 2 terabytes per second and a peak throughput of 7 terabytes per second. A significant challenge addressed is the bursty nature of checkpoint writes, which can saturate the storage fabric. Checkpointing is essential for saving each GPU's model state, ranging from 1 megabyte to 4 gigabytes per GPU, to facilitate recovery and debugging. The goal is to minimize GPU pause time during checkpointing and increase checkpoint frequency to reduce lost work after recovery. Network configuration. The Llama 3405B model utilizes RDMA over Converged Ethernet, ROS, fabric, based on Arista 7800 and Minipack 2 Open Compute Project rack switches. Smaller models in the Llama 3 family use NVIDIA Quantum 2 InfiniBand fabric. Both network types employ 400 gigabits per second interconnects between GPUs, tuned to provide equivalent performance for large training workloads. Network topology. The ROCEBASEDAI cluster comprises 24,000 GPUs connected by a 3-layer CLO network. Each rack at the bottom layer hosts 16 GPUs split between 2 servers, connected by a Minipack 2 top of the rack switch. The middle layer connects 192 racks via cluster switches to form a pod of 3,072 GPUs with full bisection bandwidth. The top layer connects 8 such pods within the same datacenter via aggregation switches, forming a cluster of 24,000 GPUs. However, the aggregation layer has an oversubscription ratio of 1:7, necessitating optimization of model parallelism methods and training job scheduling to minimize cross-pod network communication. Load balancing. Traditional load balancing methods like equal cost multipath, ECMP, routing are insufficient for the large network flows produced by LLM training. To address this, 2 techniques are employed. 1. The collective library creates 16 network flows between 2 GPUs, reducing traffic per flow and increasing the number of flows. 2. This approach ensures better load distribution across available network paths, enhancing overall network efficiency. In summary, the page meticulously details the computational and network infrastructure supporting the Llama 3405B model training, emphasizing the importance of efficient resource management and network optimization to achieve high-performance outcomes on the ARC Challenge benchmark. Key points and concepts. 1. Scaling configurations and MFU. Table 4 presents various scaling configurations and their corresponding model flops utilization, MFU. for the Llama 3405B pre-training. The configurations vary in the number of GPUs, tensor parallelism, TP, context parallelism, CP, pipeline parallelism, PP, data parallelism, DP, sequence length, batch size per DP, tokens per batch, TFLOPs per GPU, and BF16 MFU. The MFU ranges from 38% to 43%, indicating efficient utilization of GPU resources. 2. Enhanced ECMP, EECMP, protocol. The EECMP protocol is introduced to balance network load by hashing additional fields in the rows header of packets, effectively distributing 16 flows across different network paths. This approach mitigates congestion and enhances load balancing, crucial for large-scale training environments. 3. Congestion control. The use of deep buffer switches in the network spine helps manage transient congestion and buffering, which are common in collective communication patterns during training. This setup, combined with EECMP, allows the system to operate a 24K GPU cluster without traditional congestion control methods like data center quantized congestion notification, DCQCN. 4. 4D parallelism for model scaling. The paper describes a 4D parallelism strategy combining tensor parallelism, TP, pipeline parallelism, PP, context parallelism, CP, and data parallelism, DP, to efficiently distribute computation across GPUs. This method ensures that model parameters, optimizer states, gradients, and activations fit within each GPU's high-bandwidth memory, HBM. 5. Detailed parallelism techniques. Tensor parallelism, TP, splits weight tensors across multiple devices. Pipeline parallelism, PP, divides the model into stages processed in parallel. Context parallelism, CP, segments input context to handle long sequence lengths. Data parallelism, DP, processes data in parallel across GPUs, synchronizing after each training step. Fully sharded data parallelism, FSDP, is used to shard optimizer states and gradients, avoiding extra communication during backward passes. 6. GPU utilization. The configurations achieve a BF16 model flops utilization, MFU, of 3,843%. The slight drop in MFU with increased GPUs and DP is attributed to the need to maintain a constant global tokens per batch during training. 7. Pipeline parallelism improvements. The paper identifies challenges with existing pipeline parallelism implementations, such as batch size constraints, memory imbalance, and computation imbalance. These issues arise from the need for divisible batch sizes per GPU, uneven memory consumption across stages, and execution latency bottlenecks at the final stage. Figures and tables. Table 4 summarizes the scaling configurations and MFU for different stages of Llama 3405B pre-training. Figure 5 illustrates the implementation of 4D parallelism, though the figure itself is not provided on this page. Limitations and future work. The page highlights the need for flexible batch size adjustments and addresses memory and computation imbalances in pipeline parallelism. Future work may focus on refining these aspects to further optimize training efficiency. Conclusion. This page provides a comprehensive overview of the sophisticated techniques used to scale and optimize the training of large models like Llama 3405B. The detailed discussion on parallelism strategies, network optimizations, and GPU utilization underscores the complexity and innovation involved in modern deep learning training processes. 4D parallelism. The concept of 4D parallelism is illustrated in Figure 5. Where GPUs are divided into 4 parallelism groups. Tensor parallelism, TP, context parallelism, CP, pipeline parallelism, PP, and data parallelism, DP. In this example, 16 GPUs are configured with a group size of TP equals 2, CP equals 2, PP equals 2, and DP equals 2. Each GPU's position in the 4D parallelism space is represented as a vector, D1, D2, D3, D4, where D is the index on the ITH parallelism dimension. For instance, GPU 0 is denoted as TP0, CP0, PP0, DP0, and GPU 1 as TP1, CP0, PP0, DP0, indicating that GPU 0 and GPU 1 are in the same TP group, GPU 0 and GPU 2 are in the same CP group, and so forth. Pipeline scheduling. To address the limitations of traditional pipeline schedules, the authors propose a modified pipeline schedule, illustrated in Figure 6, that allows flexible setting of n, the number of microbatches per batch. This flexibility enables running fewer microbatches than the number of stages when constrained by batch size or more microbatches to hide point-to-point communication, optimizing between depth-first schedule, DFS, and breadth-first schedule, BFS, for communication and memory efficiency. The pipeline is balanced by reducing one transformer layer each from the first and last stages, with the first stage containing only the embedding and the last stage containing only the output projection and loss calculation. Interleaved schedule and asynchronous communication. To minimize pipeline bubbles, an interleaved schedule, Narayanan et al. 2021, with V pipeline stages on one pipeline rank is used, resulting in an overall pipeline bubble ratio of pp1, vm. Asynchronous point-to-point communication in PP is adopted to speed up training, especially when document masks introduce computation imbalances. The torch_NCCL_avoid_record_streams flag is enabled to reduce memory usage from asynchronous communication. Additionally, proactive deallocation of tensors that are no longer needed for future computation is implemented to further reduce memory costs, allowing pre-training of Llama 3 on sequences of 8K tokens without activation checkpointing. Context parallelism, CP. Context parallelism, CP, is utilized to improve memory efficiency when scaling the context length of Llama 3, enabling training on sequences up to 128K in length. In CP, the input sequence is partitioned into two CP chunks, with each CP rank receiving two chunks for better load balancing. The ITH CP rank receives both the ITH and the two CP1 ITH chunks. Unlike existing CP implementations that use a ring-like structure for overlapping communication and computation, the authors adopt an all-gather-based method. This involves first all-gathering the key, K, and value, V, tensors, then computing the attention output for the local query, Q, tensor chunk. Despite the exposed all-gather communication latency, this approach is preferred for its flexibility in supporting different types of attention masks, such as the document mask. Conclusion. The page concludes by highlighting the significant optimizations and novel approaches in pipeline scheduling and context parallelism, which collectively enhance the training efficiency and scalability of the Llama 3 model. These innovations address key challenges in large-scale model training, such as memory efficiency, communication overhead, and load balancing, paving the way for future advancements in the field. Pipeline parallelism. Figure 6 illustrates the pipeline parallelism in Llama 3, which partitions 8 pipeline stages, 0 to 7, across 4 pipeline ranks, PP ranks 0 to 3. Each GPU rank handles 2 stages, e.g., rank 0 runs stages 0 and 4. The figure uses colored blocks to represent a sequence of microbatches, with M denoting the total number of microbatches and N the number of continuous microbatches for the same stage's forward or backward pass. A key insight is the tunability of N, which allows for optimization based on specific requirements. Network-aware parallelism configuration. The paper discusses the optimization of parallelism dimensions, tensor parallelism, TP, channel parallelism, CP, pipeline parallelism, PP, and data parallelism, DP, for network communication. The order, TP, CP, PP, DP, is chosen to minimize communication overhead, with the innermost parallelism, TP, requiring the highest network bandwidth and lowest latency, typically constrained within the same server. DP, being the outermost, can tolerate higher latency by asynchronously prefetching sharded model weights and reducing gradients. The authors developed a memory consumption estimator and a performance projection tool to explore various parallelism configurations, effectively identifying memory gaps and projecting overall training performance. Numerical stability. To ensure training stability, the authors compared training loss across different parallelism setups and addressed several numerical issues. They employed FP32 gradient accumulation during backward computation over multiple microbatches and reduced scatter gradients in FP32 across data parallel workers in FSDP. For intermediate tensors used multiple times in forward computation, backward gradients are also accumulated in FP32, ensuring numerical stability and training convergence. Collective communication. The collective communication library for Llama 3 is based on a fork of NVIDIA's NCCL library, named NCCLX, which enhances performance, especially for higher latency networks. The order of parallelism dimensions, TP, CP, PP, DP, is reiterated, with DP corresponding to FSDP. The original NCCL collectives, all gather and reduce scatter in FSDP, and point-to-point in PP, require data chunking and staged data copy, leading to inefficiencies such as numerous small control messages, extra memory copy operations, and additional GPU cycles for communication. Llama 3 addresses some of these inefficiencies by tuning chunking and data transfer to fit network latencies, which can be as high as tens of microseconds in large clusters. Small control messages are prioritized to avoid head-of-line blocking in deep buffer core switches. Future work involves deeper changes in NCCLX to holistically address these inefficiencies. In summary, this page provides a detailed examination of the parallelism strategies and communication optimizations in Llama 3, highlighting the technical challenges and solutions implemented to enhance training performance and stability. Root cause categorization of interruptions. Table 5 categorizes the unexpected interruptions, revealing that 78% were due to confirmed or suspected hardware issues. The breakdown is as follows. Faulty GPU, 148 interruptions, 30.1%, GPU HBM3 memory, 72 interruptions, 17.2%. Software bug, 54 interruptions, 12.9%, network switch, cable, 35 interruptions, 8.4%. Host maintenance, unplanned, 32 interruptions, 7.6%, GPU SRAM memory, 19 interruptions, 4.5%, GPU system processor, 17 interruptions, 4.1%, NIC, 7 interruptions, 1.7%, NCCL watchdog timeouts, 7 interruptions, 1.7%. Silent data corruption, 6 interruptions, 1.4%, GPU thermal interface plus sensor, 6 interruptions, 1.4%, SSD, 3 interruptions, 0.7%. Power supply, 3 interruptions, 0.7%. Server chassis, 2 interruptions, 0.5%. I/O expansion board, 2 interruptions, 0.5%. Dependency, 2 interruptions, 0.5%, CPU, 2 interruptions, 0.5%. System memory, 2 interruptions, 0.5%. Reliability and operational challenges. The complexity of managing 16K GPU training is highlighted, noting that it surpasses the challenges of larger CPU clusters. The synchronous nature of the training process exacerbates fault tolerance issues, as a single GPU failure can necessitate a complete job restart. Despite these challenges, the team achieved over 90% effective training time, even with daily interruptions due to automated cluster maintenance. Interruptions and mitigation strategies. During the 54-day period, 466 job interruptions were recorded, with 47 being planned, e.g., firmware upgrades, configuration updates. The remaining 419 were unexpected, predominantly due to hardware issues, particularly GPU-related problems, which accounted for 58.7% of all unexpected interruptions. Notably, manual intervention was required only 3 times, with automation handling the rest. To enhance effective training time, the team focused on reducing job startup and checkpointing times and developed tools for rapid diagnosis and problem resolution. A key tool mentioned is PyTorch's built-in NCCL flight recorder, which captures collective metadata and stack traces into a ring buffer. This tool is crucial for diagnosing hangs and performance issues at scale, especially concerning NCCLX. It records every communication event and the duration of each collective operation, and automatically dumps tracing data on NCCLX watchdog or heartbeat timeout. Debugging and network challenges. Debugging large-scale training is complicated by the mixed use of NVLink and ROS in the network. NVLink data transfers, typically executed through load, store operations by CUDA kernels, can fail without returning clear error codes, manifesting as stalled operations. NCCLX enhances the speed and accuracy of failure diagnosis in such scenarios. Conclusion. This page provides a detailed account of the operational challenges and mitigation strategies during the Llama 3405B pre-training phase. It underscores the importance of robust diagnostic tools and automation in managing large-scale GPU training environments, highlighting the significant role of hardware reliability in overall system performance. The page also addresses the challenge of hardware-induced stragglers, which are slow-performing GPUs that can significantly impact overall performance. Tools have been developed to prioritize and identify problematic communications from selected process groups, effectively pinpointing stragglers by investigating top suspects. An interesting observation noted is the impact of environmental factors, such as diurnal temperature variations, on training performance. For instance, a 12% throughput variation was observed in the Llama 3405B model due to midday temperature increases affecting GPU dynamic voltage and frequency scaling. Additionally, the simultaneous power consumption changes by tens of thousands of GPUs during training can cause significant power fluctuations, posing challenges for data center power grids. The page then transitions to the training recipe for pre-training the Llama 3405B model, which consists of three main stages: initial pre-training, long-context pre-training, and annealing. The initial pre-training employs a cosine learning rate schedule with a peak learning rate of 8 times 10^5, a linear warm-up of 8,000 steps, and a decay to 8 times 10^7 over 1,200,000 training steps. The batch size is initially set to 4M tokens and sequences of 4,096 tokens, doubling at specific milestones to improve efficiency and stability. Adjustments to the pre-training data mix are made to enhance performance on downstream tasks. This includes increasing non-English data for better multilingual performance, upsampling mathematical data for improved reasoning, adding recent web data to extend the model's knowledge cutoff, and downsampling lower quality data subsets. The long-context pre-training stage aims to support context windows of up to 128K tokens. This stage is performed in increments to manage the quadratic growth in compute required by self-attention layers. Successful adaptation to increased context lengths is assessed by the model's performance on short context evaluations and its ability to solve needle in a haystack tasks. The context length is increased in 6 stages, starting from 8K to 128K tokens, using approximately 800B training tokens. This page provides a comprehensive overview of the technical challenges and methodologies employed in scaling and training large language models, emphasizing the importance of system design, environmental considerations, and adaptive training strategies. Figure 7 is referenced at the beginning, illustrating the overall post-training approach for Llama 3. This figure encapsulates the sequential steps of rejection sampling, supervised fine-tuning, SFT, and direct preference optimization, DPO, which are elaborated upon in the text. Section 3.4.3 Annealing describes the final phase of pre-training, where the learning rate is linearly annealed to 0 over the last 40 million tokens, while maintaining a context length of 128K tokens. This phase also involves adjusting the data mix to upsample high-quality data sources, as detailed in Section 3.1.3. Additionally, polyac averaging, polyac, 1991, is employed to compute the average of model checkpoints during annealing, resulting in the final pre-trained model. Section 4 Post-training outlines the process of aligning Llama 3 models with human feedback through multiple rounds of post-training. This involves supervised fine-tuning, SFT, followed by direct preference optimization, DPO, on examples collected via human annotations or synthetic generation. The post-training modeling and data approaches are further detailed in sections 4.1 and 4.2, with custom data curation strategies discussed in section 4.3 to enhance various capabilities such as reasoning, coding, factuality, multilingualism, tool use, long context handling, and precise instruction following. Section 4.1 modeling delves into the backbone of the post-training strategy, which comprises a reward model and a language model. Initially, a reward model is trained on top of the pre-trained checkpoint using human annotated preference data, section 4.1.2. Subsequently, the pre-trained checkpoints undergo supervised fine-tuning, SFT, section 4.1.3, and further alignment through direct preference optimization, DPO, section 4.1.4. This process is visually represented in Figure 7. The modeling procedure primarily applies to Llama 3405B, referred to simply as Llama 3 for brevity. Section 4.1.1 chat dialog format emphasizes the necessity of defining a chat dialog protocol to tune LLMs for human-AI interaction. This protocol enables the model to comprehend human instructions and perform conversational tasks. Llama 3 introduces new capabilities, such as tool use, section 4.3.5, which may necessitate generating multiple messages and sending them sequentially. The page concludes by noting that the term post-training encompasses any model training that occurs outside of the pre-training phase. In summary, this page provides a comprehensive overview of the post-training strategies for Llama 3, highlighting the importance of human feedback alignment through SFT and DPO, the role of reward models, and the introduction of new capabilities in the chat dialog format. The detailed methodologies and references to specific sections ensure a thorough understanding of the post-training process. Multi-message chat protocol. The authors introduce a novel multi-message chat protocol designed to handle messages from different sources, e.g., user, Ipython, within a single dialog turn. This protocol utilizes special header and termination tokens to indicate the source and destination of each message and to signal when to alternate between human and AI speakers. Reward modeling. The reward model, is trained on top of a pre-trained checkpoint, similar to Llama 2, but with the margin term in the loss function removed due to diminishing returns from data scaling. The training data includes preference pairs, chosen, rejected, and an additional, edited response, for some prompts, creating a clear ranking, edited greater than chosen greater than rejected. During training, prompts and responses are concatenated into a single row with responses randomly shuffled, which improves training efficiency without sacrificing accuracy. Supervised fine-tuning, SFT. The is used for rejection sampling on human annotated prompts. The pre-trained language model is then fine-tuned using a standard cross-entropy loss on target tokens, while masking loss on prompt tokens. This stage, referred to as supervised fine-tuning, SFT, involves a mix of rejections ampled data, synthetic data, and other sources. The largest models are fine-tuned with a learning rate of 1e5 over 8.5k to 9k steps, which has proven effective across different rounds and data mixes. Direct preference optimization, DPO. The SFT models are further trained using direct preference optimization, DPO, for human preference alignment. The training primarily uses recent batches of preference data collected from the best-performing models of previous rounds. DPO is preferred over on-policy algorithms like PPO due to its lower computational requirements and superior performance on instruction following benchmarks. For Llama 3, a learning rate of 1e5 and a hyperparameter of 0.1 are used. Two key algorithmic modifications are applied to DPO. 1. Masking formatting tokens. Special formatting tokens are masked out from both chosen and rejected responses in the loss function to stabilize training and prevent undesired behaviors. 2. Regularization with NLL loss. An additional negative log likelihood, NLL, loss term with a scaling coefficient of 0.2 is added to the chosen sequences to maintain desired formatting and prevent the decrease of log probability of chosen responses. Model averaging. Finally, the authors employ model averaging, combining models obtained from various experiments using different data versions or hyperparameters at each SFT, or DPO stage. This technique, inspired by prior works, Ismailov et al. 2019, Wartzman et al. 2022, Lee et al. 2022, aims to enhance model robustness and performance. Conclusion. This page builds upon previous sections by detailing the intricate processes involved in refining the AI model, highlighting novel approaches like the multi-message chat protocol and DPO modifications. It also underscores the importance of efficient training methodologies and the strategic use of data to optimize model performance. The described techniques collectively contribute to the development of a highly capable and aligned AI system. Dataset comparisons and statistics. The page begins with Table 6, which presents statistics on human preference data across various datasets. The datasets are categorized into general English, coding, multilingual, and reasoning and tools. Key metrics include the percentage of dialogues, average number of turns per dialogue, and average number of tokens per example, prompt, and response. For instance, General English comprises 81.99% of the data with an average of 4.1 turns per dialogue and 1000.4 tokens per example. This table highlights the diversity and complexity of the data used for Llama 3 alignment. Iterative rounds. The section titled 4.1.6 Iterative Rounds describes the iterative process used for data collection and model training, following the methodology of Llama 2. 6 rounds of data collection and preference annotation are conducted, with each cycle involving the sampling of synthetic data from the latest models. This iterative approach ensures continuous improvement and refinement of the model. Post-training data composition. Section 4.2 delves into the composition of post-training data, emphasizing its critical role in shaping the behavior and utility of language models. This section is subdivided into 3 parts: human annotation procedures and preference data collection, 4.2.1, SFT data composition, 4.2.2, and data quality control and cleaning, 4.2.3. Preference data annotation. In section 4.2.1, the preference data annotation process is outlined. Multiple models are deployed for annotation after each round, and 2 responses from different models are sampled for each user prompt. Annotators rate their preference for responses on a 4-level scale: significantly better, better, slightly better, or marginally better. An editing step is incorporated to further refine the preferred responses, resulting in a hierarchy of responses, edited greater than chosen greater than rejected. This process aims to enhance the quality and diversity of the training data. The statistics of preference annotations used for Llama 3 training are reported, showing an increase in the average length of prompts and responses compared to Llama 2. This indicates that Llama 3 is trained on more complex tasks. A rigorous quality analysis and human evaluation process is implemented to refine prompts and provide actionable feedback to annotators. Reward modeling and DPO training. In each round of post-training, all available preference data is used for reward modeling, while only the latest batches are used for DPO, direct preference optimization, training. Samples where the chosen response is significantly better or better than the rejected one are used for training, while similar responses are discarded. SFT data composition. Section 4.2.2 discusses the sources of fine-tuning, SFT, data, which include prompts from human annotation collections with rejections, ampled responses, and synthetic data targeting specific capabilities. This diverse data composition is crucial for enhancing the model's performance across various tasks. Conclusion. Overall, page 17 provides a comprehensive overview of the data collection, annotation, and post-training processes for Llama 3. The methodologies described ensure the collection of high-quality, diverse data, which is essential for training robust and capable language models. The iterative rounds and rigorous quality control measures highlight the meticulous approach taken to refine and improve the model continuously. Data statistics and composition. Table 7 presents a comprehensive breakdown of the statistics for the supervised fine-tuning, SFT, data used for Llama 3 alignment. The table categorizes the data into 6 distinct types: general English, code, multilingual, exam-like, reasoning and tools, and long context. Each category is analyzed based on the percentage of examples, average number of conversation turns, average number of tokens in context, and average number of tokens in the final response. Notably, the long context category, although constituting only 0.11% of the data, has an exceptionally high average number of tokens in context, 37,395.2, indicating its role in handling extensive conversational histories. Rejection sampling. The rejection sampling (RS) procedure is a critical component of the data collection process. For each prompt collected during human annotation, multiple outputs, typically between 10 and 30, are generated using the latest chat model policy. These outputs are then evaluated using a reward model to select the best candidate, following the methodology outlined by Bai et al., 2022. In later post-training rounds, system prompts are introduced to guide the RS responses to adhere to specific tones, styles, or formats, enhancing the model's versatility across different capabilities. To optimize the efficiency of rejection sampling, the paged attention mechanism, Quan et al., 2023, is employed. Paged attention improves memory efficiency by dynamically allocating key-value cache based on current capacity, thus supporting arbitrary output lengths. This approach mitigates the risk of memory swap-out by defining a maximum output length and ensuring sufficient memory availability before processing requests. Additionally, paged attention allows for the sharing of key-value cache pages across all outputs for a given prompt, resulting in a throughput improvement of over 2x during rejection sampling. Data processing and quality control. Given the predominance of model-generated data, rigorous data cleaning and quality control measures are essential. Early rounds of data collection revealed undesirable patterns, such as excessive use of emojis or overly apologetic tones. To address these issues, rule-based data removal and modification strategies are implemented. For instance, phrases like, "I'm sorry," or "I apologize," are identified and balanced within the dataset to mitigate tonal issues. Data pruning involves model-based techniques to eliminate low-quality training samples. One such technique is topic classification, where Llama 3.8b is fine-tuned into a topic classifier. This classifier is used to categorize data into both coarse-grained, e.g., mathematical reasoning, and fine-grained buckets, ensuring a more structured and high-quality dataset. Conclusion. This page builds upon previous sections by detailing the methodologies for data collection, processing, and quality control, which are crucial for the development of a robust and versatile language model like Llama 3. The use of advanced techniques such as paged attention and topic classification underscores the innovative approaches taken to enhance model performance and data quality. Future work may focus on further refining these processes and exploring additional strategies for data optimization and model alignment. Quality scoring. The quality of each sample is assessed using two primary methods: a reward model, ERM, and Llama-based signals. The RMBASED score considers data in the top quartile as high quality. For Llama-based scoring, Llama 3 is prompted to rate samples on a 3-point scale for general English data, covering accuracy, instruction following, and tone, presentation, and a 2-point scale for coding data, covering bug identification and user intention. Despite high disagreement rates between RM and Llama-based scores, combining these signals yields the best recall on internal test sets. Ultimately, examples marked as high quality by either the RM or Llama-based filter are selected. Difficulty scoring. To prioritize more complex examples, two measures of difficulty are used: Instig and Llama-based scoring. Instig involves intention tagging of SFT prompts by Llama 370b, where more intentions imply greater complexity. Additionally, Llama 3 measures the difficulty of dialogues on a 3-point scale. Semantic deduplication. Semantic deduplication is performed to eliminate redundant data. Complete dialogues are clustered using Roberta, and within each cluster, examples are sorted by a combined quality and difficulty score. A greedy selection process is then applied, retaining only those examples with a maximum cosine similarity below a certain threshold to previously seen examples in the cluster. Capabilities. The section highlights efforts to improve specific capabilities such as code, multilinguality, math and reasoning, long context, tool use, factuality, and steerability. The focus here is on code-related capabilities. Code capabilities. LLMs for code have gained significant traction since the release of tools like Copilot and Codex. For Llama 3, the goal is to enhance code generation, documentation, debugging, and review capabilities across several high-priority programming languages, including Python, Java, JavaScript, C, C++, TypeScript, Rust, PHP, HTML, CSS, SQL, and Bash, Shell. Expert training. A code expert model is trained to collect high-quality human annotations for code. This involves branching from the main pre-training run and continuing with a 1T token mix predominantly, greater than 85%, consisting of code data. This approach, similar to Code Llama, has been shown to improve domain-specific performance. Long context fine-tuning, LCFT, is performed to extend the expert's context length to 16K tokens on high-quality repo-level code data. The model is aligned using SFT and DPO data mixes primarily targeting code and is also used for rejection sampling for coding prompts. Synthetic data generation. Key issues in code generation, such as difficulty in following instructions, syntax errors, incorrect code generation, and bug fixing, are identified. While human annotation could address these issues, synthetic data generation offers a scalable and cost-effective alternative. Llama 3 and the Code Expert are used to generate a large quantity of synthetic SFT dialogues, resulting in over 2.7 million synthetic examples used during SFT. Conclusion. This page provides a comprehensive overview of the methodologies used to enhance the quality and complexity of training data for Llama 3, with a particular focus on improving code-related capabilities through expert training and synthetic data generation. The strategies discussed aim to ensure high-quality, diverse, and complex training data, ultimately improving the performance and utility of Llama 3 in various applications. 1. Synthetic data generation. Execution feedback. Performance improvements and initial challenges. The 8B and 70B models exhibit significant performance enhancements when trained on data generated by a more competent model. However, training the Llama 3405B model on its own generated data initially proved counterproductive, even degrading performance. To mitigate this, execution feedback was introduced as a corrective mechanism, enabling the model to learn from its mistakes. Data generation process. Problem description generation. A diverse set of programming problem descriptions is generated by sampling random code snippets from various sources and prompting the model to create problems inspired by these examples. This approach ensures coverage of a wide range of topics, including those in the long-tail distribution. Wei et al., 2024. Solution generation. Llama 3 is prompted to solve each problem in a specified programming language. Incorporating general programming rules and requiring the model to explain its thought process in comments enhances the quality of the generated solutions. Correctness analysis. Ensuring the correctness of generated solutions is critical. A combination of static and dynamic analysis techniques is employed. Static analysis. Generated code is parsed and linted to catch syntax errors, uninitialized variables, non-imported functions, code style issues, and typing errors. Unit test generation and execution. The model generates unit tests for each problem and solution, which are executed in a containerized environment to catch runtime and some semantic errors. Error feedback and iterative self-correction. When a solution fails, the model is prompted to revise it using the original problem description, the faulty solution, and feedback from the parser, linter, tester. The model can either fix the code to pass existing tests or modify the unit tests to accommodate the generated code. Only dialogues that pass all checks are included in the final dataset for supervised fine-tuning, SFT. Approximately 20% of initially incorrect solutions self-corrected, demonstrating the model's learning from execution feedback. Fine-tuning and iterative improvement. The fine-tuning process is iterative, with each round building on the previous one, progressively refining the model's performance and generating higher quality synthetic data. 2. Synthetic data generation. Programming language translation. Addressing performance gaps. A performance gap exists between major programming languages, e.g., Python, C++, and less common ones, e.g., TypeScript, PHP, due to the disparity in training data. To bridge this gap, data from common languages is translated to less common ones using Llama 3, ensuring quality through syntax parsing, compilation, and execution. Figure 8 illustrates an example of synthetic PHP code translated from Python, significantly improving performance for less common languages as measured by the multiple benchmark, Cassano et al., 2023. 3. Synthetic data generation, back translation, enhancing coding capabilities. For capabilities where execution feedback is less informative, e.g., documentation, explanations, a multi-step back translation approach is employed. This method generated approximately 1.2 million synthetic dialogues, further enhancing the model's performance in these areas. Conclusion. This page outlines a comprehensive approach to synthetic data generation, emphasizing the importance of execution feedback, programming language translation, and back translation. These methodologies collectively enhance the model's performance, particularly in generating high-quality, diverse programming solutions and bridging gaps between different programming languages. The iterative fine-tuning process and error feedback mechanisms are crucial for continuous improvement, demonstrating the model's ability to learn and self-correct. Figures and examples. Figure 8 illustrates a code translation example where Llama 3 translates Python code into PHP. This example underscores the model's capability to augment the SFT, supervised fine-tuning, dataset with a broader range of programming languages, thereby enhancing its versatility. Figure 9 demonstrates the impact of system prompts on the quality of generated code. The left side shows code generated without system prompts, while the right side shows code generated with system prompts, highlighting improvements in readability, documentation, and overall quality. Key methodologies. 1. Generate. The process begins with prompting Llama 3 to generate data that aligns with the desired capabilities. For instance, the model is asked to add comments and doc strings to code snippets or to explain a piece of code. This step leverages the pre-training data, which includes code snippets from various programming languages. 2. Back translate. The model is then prompted to back translate the synthetically generated data to the original code. This involves generating code solely from its documentation or explanation, ensuring that the model can accurately reconstruct the original code from its descriptive elements. 3. Filter. Using the original code as a reference, Llama 3 assesses the quality of the back-translated code. The model is asked to evaluate how faithful the generated code is to the original. Only the examples with the highest self-verification scores are included in the SFT dataset, ensuring high-quality training data. System prompt steering. During the rejection sampling process, system prompts are employed to enhance code readability, documentation, thoroughness, and specificity. This technique, as referenced from Section 7, is crucial for fine-tuning the language model. The example in Figure 9 illustrates how system prompts can significantly improve the generated code by adding necessary comments, using more informative variable names, and optimizing memory usage. Filtering training data. The page also addresses the challenge of filtering training data, particularly when dealing with rejections-ampled data that may contain quality issues such as bugs. Unlike synthetic code data, rejections-ampled responses often include a mix of natural language and code, complicating the detection of errors. This issue is further elaborated in Section 4.2.3. Connection to previous sections. The methodologies and techniques discussed on this page build upon concepts introduced in earlier sections, such as the use of system prompts, Section 7, and the challenges of filtering training data, Section 4.2.3. These connections highlight the iterative and comprehensive approach taken to refine the model's capabilities. Limitations and future work. While the page does not explicitly mention limitations or future work, the discussion of quality issues in rejections-ampled data implies ongoing challenges that need to be addressed. Future work may focus on improving the detection and filtering of errors in mixed natural language and code responses. In summary, this page provides a detailed overview of the strategies used to enhance the quality and diversity of code generated by Llama 3, emphasizing the importance of system prompts, back translation, and rigorous filtering processes. The figures and examples effectively illustrate the improvements achieved through these methodologies. Model as Judge approach. The Model as Judge approach is introduced to address the challenge of ensuring code correctness and style in user prompts, which may not always be executable. This method involves earlier versions of Llama 3 evaluating and assigning a binary score, 0 or 1, based on two criteria: code correctness and code style. Only samples achieving a perfect score of 2 are retained. Initially, this stringent filtering led to a regression in downstream benchmark performance because it disproportionately removed examples with challenging prompts. To mitigate this, the responses to some of the most challenging coding data were revised until they met the UMABEST criteria. This refinement process balanced the quality and difficulty of the coding data, optimizing downstream performance. Multilinguality. The section on multilinguality outlines the strategies employed to enhance Llama 3's capabilities in multiple languages. This includes training a specialized expert on a significantly larger corpus of multilingual data, sourcing and generating high-quality multilingual instruction tuning data for several languages: German, French, Italian, Portuguese, Hindi, Spanish, and Thai, and addressing specific challenges in multilingual language steering. Expert training. The pre-training data mix for Llama 3 contains more English tokens than non-English tokens. To collect higher quality human annotations in non-English languages, a multilingual expert model is trained by branching off the pre-training run and continuing with a data mix consisting of 90% multilingual tokens. Post-training is then performed on this expert model, which is subsequently used to collect higher quality annotations in non-English languages until pre-training is complete. Multilingual data collection. The multilingual SFT, supervised fine-tuning, data is derived from various sources, with the overall distribution being 2.4% human annotations, 44.2% data from other NLP tasks, 18.8% rejection sample data, and 34.6% translated reasoning data. Human annotations. High-quality, manually annotated data is collected from linguists and native speakers, focusing on open-ended prompts that represent real-world use cases. Data from other NLP tasks. Multilingual training data from other tasks is rewritten into dialogue format. Examples include data from Examska and Conic 10K. Parallel texts from Global Voices and Wikimedia are also used, with lid-based filtering and Blazor 2.0 applied to remove low-quality data. A multilingual template inspired by Wei et al. Is used to simulate real-life conversations. Rejection sample data. Rejection sampling is applied to human annotated prompts to generate high-quality samples for fine-tuning. The temperature hyperparameter is varied to balance creativity and naturalness in responses, with a final constant value of 0.6 used. Specialized system prompts improve response format, structure, and readability. Translated data. Machine-translated data is generally avoided to prevent translationese and various biases. However, an exception is made for synthetic quantitative reasoning data to improve performance in non-English languages. Conclusion. This page provides a comprehensive overview of the methodologies and strategies employed to enhance the Llama 3 model's code evaluation and multilingual capabilities. The Model as Judge approach ensures high-quality coding data, while the multilingual strategies significantly improve the model's performance across various languages. The detailed processes and considerations outlined here are crucial for understanding the advancements and challenges in developing a robust, multilingual AI model. Key challenges in mathematical reasoning. 1. Lack of prompts. As mathematical problems become more complex, the availability of valid prompts for supervised fine-tuning, SFT, diminishes. This scarcity hampers the creation of diverse and representative training datasets necessary for teaching models various mathematical skills. Yu et al. 2023. Yu et al. 2023. Luo et al. 2023. Mitra et al. 2024. Xiao et al. 2024. Yu et al. 2024b. 2. Lack of ground truth chain of thought. Effective reasoning requires step-by-step solutions to guide the model through the problem-solving process. However, there is often a shortage of these ground truth chains, which are crucial for breaking down problems and reaching correct answers. Wei et al. 2022 c. Seligman et al. 2022. 3. Incorrect intermediate steps. Model-generated chains of thought can contain inaccuracies in intermediate steps, leading to incorrect final answers. This issue necessitates mechanisms to ensure the correctness of these steps. Cobb et al. 2021. Uesato et al. 2022. Lightman et al. 2023. Wang et al. 2023a. 4. Teaching models to use external tools. Enhancing models to utilize external tools, such as code interpreters, can significantly improve their problem-solving abilities by allowing them to interleave code and text reasoning. Gao et al. 2023. Chen et al. 2022. Go et al. 2023. 5. Discrepancy between training and inference. There is often a mismatch between the model's training environment and its real-world usage during inference. Ensuring consistency between these phases is crucial for maintaining reasoning performance. Methodologies to address challenges. 1. Addressing the lack of prompts. Relevant pre-training data from mathematical contexts is converted into a question-answer format for supervised fine-tuning. Additionally, a taxonomy of mathematical skills is created, and humans are asked to provide relevant prompts to address areas where the model underperforms. Didolkar et al. 2024. 2. Augmenting training data with stepwise reasoning traces. Llama 3 is used to generate step-by-step solutions for prompts, which are then filtered based on the correctness of the final answer. Li et al. 2024a. Self-verification by Llama 3 ensures the validity of these solutions, improving the quality of fine-tuning data. 3. Filtering incorrect reasoning traces. Outcome and stepwise reward models are trained to filter out incorrect intermediate reasoning steps. Lightman et al. 2023. Wang et al. 2023a. For more challenging prompts, Monte Carlo tree search, MCTS, with learned stepwise reward models is used to generate valid reasoning traces. Xie et al. 2024. 4. Interleaving code and text reasoning. Llama 3 is prompted to solve reasoning problems using a combination of textual reasoning and associated Python code. Code execution serves as a feedback signal to eliminate invalid reasoning chains, ensuring the correctness of the reasoning process. Go et al. 2023. 5. Learning from feedback and mistakes. Incorrect generations are used to simulate human feedback, prompting Llama 3 to perform error correction and improve its reasoning capabilities. Conclusion. This page outlines a comprehensive approach to enhancing mathematical reasoning in machine learning models by addressing key challenges and employing sophisticated methodologies. The strategies include sourcing diverse prompts, generating and verifying stepwise reasoning traces, filtering incorrect data, interleaving code and text reasoning, and learning from feedback. These efforts aim to create robust models capable of performing complex mathematical reasoning with high accuracy. Long context. Context length extension. The Llama 3 model's context length is extended from 8K tokens to 128K tokens during the final pre-training stage. This extension necessitates a careful balance between short and long context capabilities during fine-tuning, as detailed in Section 3.4. SFT and synthetic data generation. The naive application of the existing supervised fine-tuning (SFT) recipe with only short context data led to significant regressions in long context capabilities. To address this, synthetic data is predominantly used due to the impracticality of human annotation for lengthy contexts. Synthetic data generation leverages earlier versions of Llama 3 and focuses on key long context use cases such as question answering, summarization, and code reasoning. Question answering. Long documents from the pre-training mix are split into 8K token chunks. An earlier Llama 3 model generates QA pairs based on these chunks, with the entire document used as context during training. Summarization. Hierarchical summarization is applied, where 8K token chunks are first summarized, followed by summarizing these summaries. The model is trained to preserve important details while summarizing entire documents. QA pairs are also generated from these summaries to ensure a global understanding of the document. Long context code reasoning. Python files are parsed to identify import statements and dependencies. Key files, referenced by at least 5 other files, are removed, and the model is prompted to identify dependent files and generate the missing code. Synthetic samples are categorized by sequence length, 16K, 32K, 64K, and 128K, to target specific input lengths. Ablation studies reveal that mixing 0.1% of synthetically generated long-context data with short-context data optimizes performance across both benchmarks. DPO, direct preference optimization, using only short-context training data in DPO did not negatively impact long-context performance, provided the SFT model is proficient in long-context tasks. This is attributed to fewer optimizer steps in DPO compared to SFT. Consequently, the standard short context recipe is maintained for DPO on top of long context SFT checkpoints. Tool use. Expanding task range. Training LLMs to use tools like search engines and code interpreters significantly broadens their task-solving capabilities, transforming them from pure chat models to general assistants. Search engine. Llama 3 is trained to use Brave search to answer questions about recent events or retrieve specific information from the web, especially beyond its knowledge cutoff. Python interpreter. The model can generate and execute code for complex computations, read user-uploaded files, and perform tasks such as question answering, summarization, data analysis, or visualization. Summary. This page highlights the innovative approaches in extending Llama 3's context length and integrating tool usage to enhance its capabilities. The use of synthetic data for long-context tasks and the strategic application of DPO are particularly noteworthy. These methodologies ensure that Llama 3 can handle a wide range of tasks efficiently, making it a versatile and powerful model in the realm of machine learning and artificial intelligence. This section describes the implementation and training of Llama 3's tool usage capabilities, particularly its integration with the Wolfram Alpha API for solving complex queries. It details the methods used to develop and refine these capabilities, including the use of Python objects, human annotations, and synthetic data generation for both single-step and multi-step tool use. Additionally, it outlines the process for creating datasets and annotating various file types to enhance the model's performance in diverse scenarios. The page begins with a description of Figure 10, which illustrates an example of Llama 3 performing multi-step planning, reasoning, and tool calling to solve a task. This figure underscores the model's capability to handle complex, multi-step processes. The authors discuss augmenting synthetic data with various system prompts to teach the model to use tools only when necessary. This involves training the model to avoid calling tools for simple queries by incorporating easy math or question-answering datasets. Burant et al. 2013. Konsul-Kedziorsky et al. 2016. Joshi et al. 2017. Amini et al. 2019. And their responses without tools, even when tools are activated in the system prompt. This approach aims to refine the model's decision-making process regarding tool usage. The concept of zero-shot tool use, also referred to as function calling, is introduced. The authors enhance Llama 3's zero-shot tool usabilities by fine-tuning it on a large and diverse set of partly synthetic tuples, which include function definitions, user queries, and corresponding calls. The model is then evaluated on a set of unseen tools to assess its generalization capabilities. The paper outlines 3 types of function calling. 1. Single function calling. Simple, straightforward function calls. 2. Nested function calling. Function calls passed as arguments to other functions. 3. Parallel function calling. The model returns a list of independent function calls. Generating a diverse set of functions, queries, and ground truths is challenging. The authors address this by mining the stack, Kosatkov et al. 2022, to ground synthetic user queries in real functions. This involves extracting function calls and their definitions, cleaning and filtering them, and using Llama 3 to generate natural language queries corresponding to the function calls. The paper also discusses multiturn function calling, where synthetic data for multiturn dialogues with function calls is generated. This follows a protocol similar to Lee et al. 2023b, involving multiple agents that generate domains, APIs, user queries, API calls, and responses. These agents, all variants of Llama 3, are prompted differently based on their roles and collaborate in a step-by-step manner to ensure the generated data covers diverse domains and realistic APIs. Section 4.3.6 addresses the issue of factuality, highlighting that hallucinations remain a significant challenge for large language models. These models tend to be overconfident, even in domains where they lack knowledge, leading to potential risks such as the spread of misinformation. The authors acknowledge that factuality encompasses more than just hallucinations but adopt a hallucination-first approach in their analysis. In summary, this page provides a comprehensive overview of the methodologies employed to enhance Llama 3's tool usage capabilities, the challenges of generating diverse and realistic data, and the ongoing issue of maintaining factuality in large language models. The primary technique employed is a knowledge-probing method that leverages Llama 3's in-context learning capabilities. The process for generating alignment data involves several key steps. 1. Data extraction. A snippet of data is extracted from the pre-training dataset. 2. Question generation. A factual question related to the extracted snippet is generated by prompting Llama 3. 3. Response sampling. Llama 3 generates multiple responses to the question. 4. Correctness scoring. The correctness of these responses is evaluated using the original context as a reference, with Llama 3 acting as the judge. 5. Informativeness scoring. The informativeness of the responses is also scored, again using Llama 3 as the judge. 6. Refusal generation. For responses that are consistently informative but incorrect, Llama 3 generates a refusal to answer. This data generation process is designed to encourage the model to answer only those questions it has knowledge about and to refuse to answer questions it is unsure about. This is particularly important given that pre-training data can sometimes be factually inconsistent or incorrect. To address this, the researchers also collect a limited set of labeled factuality data, especially for sensitive topics where contradictory or incorrect statements are common. The page includes Figure 11, which illustrates the process of file uploads and provides an example of Llama 3 performing analysis and visualization of an uploaded file. This figure likely serves to contextualize the described methodology within a practical application, demonstrating the model's capabilities in handling real-world data inputs. The described methodology builds upon previous pages by detailing the specific steps and techniques used to align the model's knowledge post-training. It highlights the novel idea of using the model itself as a judge for correctness and informativeness, which is a significant departure from traditional external evaluation methods. In terms of limitations, the page acknowledges that the pre-training data is not always factually consistent or correct, which necessitates the collection of additional labeled factuality data. This indicates an area for future work, where improving the quality and consistency of pre-training data could further enhance the model's performance. Overall, the page provides a comprehensive overview of a sophisticated technique for aligning a language model's knowledge post-training, emphasizing the importance of factual consistency and the model's ability to self-assess its responses. This page from an academic paper discusses the concept of steerability in the context of the Llama 3 model, emphasizing the importance of directing the model's actions to meet specific developer and user requirements. It details the process of enhancing steerability through system prompts and natural language instructions, and describes the data collection and modeling techniques used to improve this aspect. Additionally, the page outlines the evaluation results of Llama 3, comparing its performance with other models on various benchmarks, including common sense reasoning, knowledge, reading comprehension, and more. Experimental setup. The evaluation involves computing scores for Llama 3 models and other comparable pre-trained models. The scores are either recomputed using the author's pipeline or taken from reported numbers, ensuring a fair comparison by selecting the best score under comparable or conservative settings. However, for some models, recomputation is not feasible due to the unavailability of pre-trained models or API limitations, particularly for Llama 3405B. Consequently, category averages for Llama 3405B are not reported. Significance values. The page discusses the variance in benchmark scores due to factors like few-shot demonstrations, random seeds, and batch size, which complicates the determination of statistical significance between models. To address this, scores are reported with 95% confidence intervals, CIS, for variance stemming from benchmark data selection. The analytical formula used for computing CIS is text, C_text, analytic, S, equals 1.96 times SQRT, frac, S, times 1S, N, where S is the benchmark score and N is the sample size. These CIS are lower bounds on the actual variance, as they do not account for all sources of variance. CIs are omitted for metrics that are not simple averages. Results for 8B and 70B models. Figure 12 illustrates the average performance of Llama 3 8B and 70B models across various benchmarks, including common sense reasoning, knowledge, reading comprehension, math and reasoning, and code. The results indicate that Llama 3 8B outperforms competing models in nearly every category, both in terms of per-category win rate and average performance. Llama 3 70B shows significant improvements over its predecessor, Llama 2 70B, on most benchmarks, except for common sense benchmarks, which may be saturated. Additionally, Llama 3 70B surpasses Mixtral 8 by 22B. Detailed results. Tables 9 through 14 present detailed benchmark performance for Llama 3 8B, 70B, and 405B models across various tasks, including reading comprehension, coding, common sense understanding, mathematical reasoning, and general tasks. These tables compare Llama 3's performance with other models, providing a granular view of its capabilities. Limitations and future work. The page acknowledges limitations in recomputing benchmark values for certain models and the challenges in ensuring fair comparisons due to variance in experimental setups. Future work may involve addressing these limitations and exploring additional benchmarks to further validate the performance of Llama 3 models. In summary, this page details the rigorous evaluation framework for Llama 3 models, highlighting their superior performance across multiple benchmarks while also addressing the inherent challenges in benchmarking and statistical significance. Performance analysis. Reading comprehension. The performance of the models on reading comprehension tasks is summarized in Table 9. The tasks include squad, quack, and race, with results presented as mean accuracies along with 95% confidence intervals. Key observations include: Llama 3 8B achieves 77.0% on squad, 44.9% on quack, and 54.3% on race. Mistral 7B scores slightly lower with 73.2% on squad, 44.7% on quack, and 53.0% on race. Llama 7B shows a higher performance on squad, 81.8%, but lower on quack, 42.4%, and race, 48.8%. Llama 3 70B matches Llama 7B on squad, 81.8%, and performs better on quack, 51.1%, and race, 59.0%. Mixtral 8 by 22B outperforms others on squad, 84.1%, and race, 59.2%, but matches Llama 3 8B on quack, 44.9%. Llama 3405B shows competitive performance with 81.8% on squad, 53.6% on quack, and 58.1% on race. Coding tasks. Table 10 presents the performance on coding tasks, specifically human eval and MBPP. Llama 3 8B scores 37.2% on human eval and 47.6% on MBPP. Mistral 7B achieves 30.5% on human eval and 47.5% on MBPP. Llama 7B scores 32.3% on human eval and 44.4% on MBPP. Llama 3 70B shows significant improvement with 58.5% on human eval and 66.2% on MBPP. Mixtral 8 by 22B scores 45.1% on human eval and 71.2% on MBPP. Llama 3405B leads with 61.0% on human eval and 73.4% on MBPP. GPT-4 achieves 67.0% on human eval. Nemotron 4340B scores 57.3% on human eval. Gemini Ultra tops the chart with 74.4% on human eval. Model robustness. The robustness of the pre-trained models is evaluated using the MMLU benchmark, focusing on their sensitivity to various design choices in multiple-choice question (MCQ) setups. The robustness factors considered include: few-shot label bias. Investigates the impact of label distribution in four-shot examples, following methodologies from Jung et al. 2023, and Weber et al. 2023a. Label variance. Examines how different label variants affect model performance. Answer order. Assesses the sensitivity of models to the order of answer choices. Prompt format. Evaluates the impact of different prompt formats on model performance. Figures and tables. Figure 12 illustrates the performance of pre-trained Llama 3 models, 8B and 70B, on various pre-training benchmarks, aggregated by capability category. Table 9 summarizes the performance of models on reading comprehension tasks. Table 10 details the performance on coding tasks. Conclusion. This page highlights the competitive performance of Llama 3405B, particularly in coding tasks, and underscores the importance of robustness in model evaluation. The analysis sets the stage for more comprehensive results on long-context tasks in Section 5.2, emphasizing the need for robust evaluation methodologies to ensure reliable model performance across different setups. Common sense understanding. Table 11 evaluates models on 5 common sense understanding tasks: Common Sense QA, PIQA, Sika, Open Book QA, and Winagrande. The models compared include Llama 3, 8B, 70B, 405B, Mistral 7B, Gemma 7B, Mixtral 822B, GPT-4, and Nemotron 4340B. Key observations include: Llama 3405B achieves the highest performance in Common Sense QA, 85.8, and PIQA, 85.6, indicating its superior ability in these tasks. Mixtral 822B and Llama 370B also show strong performance, particularly in PIQA and Winagrande. Nemotron 4340B outperforms others in Winagrande with a score of 89.5, suggesting its robustness in this specific task. Math and reasoning. Table 12 assesses models on GSM-8K, Math, ARCC, Drop, and WorldSense tasks. The models evaluated include Llama 3, 8B, 70B, 405B, Mistral 7B, Gemma 7B, Mixtral 822B, GPT-4, Nemotron 4340B, and Gemini Ultra. Notable findings are: GPT-4 leads in GSM-8K, 92.0, and ARCC, 96.3, demonstrating exceptional mathematical reasoning capabilities. Llama 3405B shows strong performance across all tasks, particularly in Math, 53.8, and Drop, 84.8. Mixtral 822B and Gemini Ultra also perform well, especially in GSM-8K and Math, indicating their effectiveness in mathematical reasoning. General language tasks. Table 13 presents results on MMLU, MMLU Pro, AGIVAL, and BB Hard tasks. The models compared include Llama 3, 8B, 70B, 405B, Mistral 7B, Gemma 7B, Mixtral 822B, GPT-4, Nemotron 4340B, and Gemini Ultra. Key insights are: Llama 3405B achieves the highest scores in MMLU, 85.2, and BB Hard, 85.9, highlighting its general language understanding capabilities. GPT-4 and Nemotron 4340B also show strong performance, particularly in MMLU and BB Hard. Gemini Ultra performs well in BB Hard, 83.6, indicating its robustness in this task. Analysis and implications. The results indicate that larger models, such as Llama 3405B and GPT-4, generally outperform smaller models across various tasks, suggesting a positive correlation between model size and performance. The performance variations across different tasks highlight the strengths and weaknesses of each model, providing valuable insights for future model development and optimization. Limitations and future work. The page does not explicitly discuss limitations or future work, but the performance variability across tasks suggests areas for improvement. Future research could focus on enhancing model performance in specific tasks where current models underperform, such as Seeka and OpenBook QA. Conclusion. This page provides a detailed comparative analysis of pre-trained models on common sense understanding, math and reasoning, and general language tasks. The results underscore the importance of model size and architecture in achieving high performance, offering a benchmark for future advancements in the field. Key concepts and methodologies. 1. Label variance. The study examines how the models respond to different sets of choice tokens. The token sets include common language independent tokens, and rare tokens, section, Z, U, that lack implicit relative order. Additionally, canonical labels, A, B, C, D, and their variations, A, B, C, D, as well as numerical labels, 1, 2, 3, 4, are considered. The robustness to these label variants is crucial as it tests the model's ability to generalize across different symbolic representations. 2. Answer order. Following the methodology proposed by Wang et al. 2024a, the stability of model performance across different answer orders is evaluated. This involves remapping all answers in the dataset according to a fixed permutation. For instance, in the permutation ABCD, labels A and B remain unchanged, while labels C and D are swapped. This test assesses the model's consistency in handling reordered answer choices, which is important for understanding its robustness to input variations. 3. Prompt format. The variance in performance is evaluated across 5 different task prompts, which vary in the level of information provided. These range from simple prompts asking the model to answer the question to more complex prompts asserting the model's expertise or emphasizing the selection of the best answer. This analysis helps in understanding how different prompt structures influence model performance, which is critical for optimizing prompt design in practical applications. Figures and results. Figure 13. The left side of the figure illustrates the performance of the models with different label variants. The right side shows performance with different labels present in fewshot examples. The results indicate that the Llama 3 models exhibit high robustness to changes in multiple choice question, MCQ, labels and the structure of fewshot prompt labels. This robustness is particularly significant as it demonstrates the model's ability to maintain performance despite variations in input representation. Figure 14. The left side of the figure presents the performance across different answer orders, while the right side shows performance across different prompt formats. The findings suggest that the models are stable across different answer orders and prompt formats, further underscoring their robustness. Limitations and future work. The page does not explicitly discuss limitations or future work, but the robustness tests imply areas for further exploration, such as the impact of more complex or less structured prompts and the examination of robustness across a broader range of tasks and datasets. Conclusion. Page 32 provides a comprehensive analysis of the robustness of Llama 3 models to various design choices in the MMLU benchmark. The detailed evaluation of label variants, answer order, and prompt format highlights the model's ability to generalize and maintain performance across different conditions, which is crucial for their application in diverse real-world scenarios. The figures effectively summarize the experimental results, reinforcing the model's robustness and stability. Adversarial benchmarks. The section begins by introducing the adversarial benchmarks used to test the model's robustness. These benchmarks are designed to be particularly challenging and can reveal potential overfitting on standard benchmarks. The specific adversarial datasets used are Adversarial Squad and Dynabench Squad for question answering, GSM Plus for mathematical reasoning, Pause for paraphrase detection. The non-adversarial counterparts for these tasks are Squad, GSM 8K, and QQP, respectively. The performance of Llama 3 models with 8B, 70B, and 405B parameters is plotted in Figure 15, which compares adversarial and non-adversarial scores. The figure is divided into two parts. The left side shows results for pre-trained models, while the right side shows results for post-trained models. Each data point represents a pair of adversarial and non-adversarial datasets within a category, with the diagonal black line indicating parity between the two types of datasets. Key findings. For paraphrase detection, both pre-trained and post-trained models show resilience against the adversarial nature of PAWS, indicating a significant improvement over previous model generations. This aligns with findings from Weber et al. 2023a, suggesting that large language models, LLMs, are less prone to spurious correlations in adversarial datasets. In contrast, for mathematical reasoning and question answering, the models exhibit substantially lower performance on adversarial benchmarks compared to non-adversarial ones. This trend is consistent across both pre-trained and post-trained models, highlighting a vulnerability in these areas. Contamination analysis. The page also discusses contamination analysis, which aims to estimate the extent to which benchmark scores might be influenced by the presence of evaluation data in the pre-training corpus. The authors reference Singh et al. 2024 for an overview of various contamination methods and their associated hyperparameters. They acknowledge that these methods can suffer from false positives and negatives, and the field of contamination analysis remains an open area of research. The authors largely follow the recommendations of Singh et al. 2024 in their approach. Figures and tables. Figure 15. This figure is crucial as it visually represents the performance comparison between adversarial and non-adversarial benchmarks for different model sizes and training stages. It underscores the model's robustness, or lack thereof, in various tasks. Conclusion. This page builds upon previous discussions by providing empirical evidence of the model's performance under adversarial conditions. It highlights significant findings, such as the model's robustness in paraphrase detection and their vulnerabilities in mathematical reasoning and question answering. The contamination analysis section sets the stage for further discussions on the reliability of benchmark scores, pointing to ongoing research and methodological challenges in this area. Overall, the page provides a comprehensive evaluation of the model's adversarial robustness and introduces critical considerations for future work in contamination analysis. Performance on long context tasks. The page begins by presenting Table 14, which summarizes the performance of pre-trained Llama 3 models on long context tasks such as quality and GSM-8K. The results are provided with 95% confidence intervals, indicating the robustness of the performance metrics. For instance, the 405B model achieves a performance of 87.6 with a confidence interval of plus or minus 1.4 on quality, 5-shot, and 90.0 with a confidence interval of plus or minus 5.9 on GSM-8K, 16-shot. Contamination and performance gain estimation. Table 15 provides a comprehensive overview of the contamination levels in various evaluation datasets and the estimated performance gains due to this contamination. The contamination detection method is based on the work of Singh et al. 2024, which uses an 8-gram overlap technique to identify contaminated examples. The table lists the percentage of contaminated evaluation sets and the corresponding performance gains for different model sizes. Key observations from Table 15 include high contamination and performance gain for datasets like PIQA and HelloSwag. Significant contamination in datasets like natural questions, but with negligible performance impact. Datasets such as Squad and Math show high contamination levels but no performance gains, suggesting the need for larger NGRAMS or alternative contamination detection methods. Methodology for contamination detection. The methodology section explains the empirical selection of contamination detection methods, focusing on the difference between clean and entire datasets to estimate performance gains. The 8-gram overlap method is highlighted as effective for many datasets, with contamination thresholds, TD, selected to maximize significant performance gains across different model sizes. Results and analysis. The results section discusses the implications of the contamination analysis. It notes that while some datasets show a clear impact of contamination on performance, others do not. This variability suggests that the effectiveness of contamination detection methods may depend on the specific characteristics of each dataset. Post-trained language model evaluation. The page transitions to discussing the evaluation of post-trained Llama 3 models. It mentions that the post-training data has been decontaminated using exact match techniques with benchmark prompts. The evaluation includes both standard academic benchmarks and extensive human evaluations, with details provided in Section 5.3. Experimental setup. The experimental setup for post-training mirrors that of the pre-training phase. A comparative analysis is conducted between Llama 3 and other models of similar size and capability. The paper emphasizes the importance of evaluating other models independently to ensure a fair comparison, with additional details available in the referenced sections. Conclusion. In summary, this page provides a thorough examination of the performance and contamination issues in pre-trained and post-trained Llama 3 models. It highlights the variability in contamination impact across different datasets and underscores the need for tailored contamination detection methods. The post-training evaluation setup aims to ensure rigorous and fair comparisons with other models, contributing to the overall robustness of the research findings. Benchmarks overview. The page begins by listing various benchmarks categorized by their specific focus areas, such as general knowledge, math and reasoning, code, multilinguality, TULUs, and long context. These benchmarks are essential for evaluating the post-training performance of Llama 3 models. Table 16, referenced but not shown, presumably provides a comprehensive overview of these benchmarks. General knowledge and instruction following benchmarks. General knowledge. The evaluation of Llama 3 on general knowledge is conducted using MMLU, Hendricks et al. 2021a, and MMLU Pro, Wang et al. 2024b. MMLU is used to assess the model's capability in knowledge-based question answering, reporting the macro average of subtask accuracy under a 5-shot standard setting without chain of thought, COT. MMLU Pro extends MMLU by incorporating more challenging, reasoning-focused questions, eliminating noisy questions, and expanding the choice set from 4 to 10 options. For MMLU Pro, a 5-shot COT setting is used. The tasks are formatted as generation tasks, similar to simple evals, OpenAI, 2024. The results, summarized in Table 2, indicate that the 8B and 70B variants of Llama 3 outperform other models of similar sizes on both general knowledge tasks. The 405B model surpasses GPT-4 and Nemotron 4340B, with Claude 3.5 Sonnet leading among larger models. Instruction following. The instruction following capability of Llama 3 is evaluated using IF-Eval, Zhou et al. 2023, which consists of approximately 500 verifiable instructions, such as write in more than 400 words. These instructions can be verified by heuristics. The evaluation reports the average of prompt level and instruction level accuracy under both strict and loose constraints, as shown in Table 2. All Llama 3 variants outperform comparable models across IF-Eval. Proficiency exams. The page also discusses the evaluation of Llama 3 models on various proficiency exams designed to test human capabilities. These exams include GRE, Official GRE Practice Test 1 and 2 from the Educational Testing Services. LSAT, Official Prep Test 71, 73, 80, and 93. SAT, 8 exams from the Official SAT Study Guide Edition 2018. AP, 1 official practice exam per subject. GMAT, Official GMAT online exam. The questions in these exams are a mix of multiple-choice questions, MCQs, and generation questions, excluding those accompanied by images. For GRE exams with questions that have multiple correct options, the model's output is considered correct only if all correct options are selected. Summary. This page provides a comprehensive evaluation framework for Llama 3 models, detailing the benchmarks and methodologies used to assess their performance in general knowledge, instruction following, and proficiency exams. The results indicate that Llama 3 models, particularly the larger variants, perform exceptionally well compared to other models, highlighting their advanced capabilities in these areas. The detailed breakdown of benchmarks and evaluation criteria ensures a robust assessment of the model's performance, providing valuable insights for further research and development. Proficiency exams performance. The page begins with Table 17, which summarizes the performance of these models on a variety of exams, including the LSAT, SAT, Reading and Math, GMAT, Quantitative and Verbal, GRE, Physics, Quantitative, and Verbal, and several Advanced Placement, AP, exams. The table reports accuracy for most exams, except for the GRE, where scaled scores out of 170 are provided. Key observations from Table 17 include: the Llama 3405B model performs comparably to Claude 3.5 Sonnet and GPT-4o across most exams. The Llama 370B model shows superior performance, significantly outperforming GPT 3.5 Turbo and often surpassing Nemotron 4340B. For AP exams, the Llama 3 models generally achieve high accuracy, with the 70B and 405B models often scoring above 90%. Coding benchmarks. The section titled 5.2.3 Coding Benchmarks evaluates the Llama 3 models on code generation tasks using popular Python and multi-programming language benchmarks. The effectiveness of the models is measured using the pass at n metric, which assesses the pass rate for a set of unit tests among n generations, with pass at 1 being reported. Python code generation. The benchmarks used for Python code generation include Human Eval, Chen et al. 2021, focuses on generating simple, self-contained functions. MBPP, Austin et al. 2021, another benchmark for Python code generation. Human Eval Plus, Liu et al. 2024a, an enhanced version of Human Eval with additional tests to avoid false positives. MBPP Eval Plus, version 0.2.0, a curated selection of 378 well-formed problems from the original MBPP dataset. The results for these benchmarks are reported in Table 18, not shown on this page. Preliminary observations indicate that the Llama 3.8b and 70b models outperform other models on these Python benchmarks. Summary and implications. The page highlights the competitive performance of the Llama 3 models, particularly the 70b and 405b variants, across a wide range of standardized exams and coding tasks. The results suggest that these models are not only capable of understanding and generating natural language but also excel in specialized tasks such as code generation. Limitations and future work. While the page does not explicitly discuss limitations or future work, the context implies that further improvements could be made in enhancing the robustness and accuracy of the models, particularly in more complex or less structured tasks. Conclusion. Overall, the page provides a comprehensive evaluation of the Llama 3 models, demonstrating their strong performance across various domains. This evaluation is crucial for stakeholders and researchers looking to understand the capabilities and potential applications of these advanced LLMs. Code generation benchmarks. The first part of the page discusses the performance of different models on code generation tasks, specifically on the Human Eval, Human Eval Plus, and MBPP benchmarks. Table 18 provides pass at 1 scores for these benchmarks, which measure the accuracy of the first generated solution. The models evaluated include Llama 3, with varying parameter sizes, Gemma 2, Mistral, Mixtral, GPT 3.5 Turbo, GPT-4, GPT-4o, Claude 3.5 Sonnet, and Nemotron 4. Key observations from Table 18. Llama 3405B and GPT-4o exhibit the highest performance across all benchmarks, with Llama 3405B achieving a pass at 1 score of 89.0 on Human Eval. Smaller models like Mistral 7B and Gemma 2.9B show significantly lower performance, indicating a strong correlation between model size and code generation capability. Claude 3.5 Sonnet also performs exceptionally well, particularly on the Human Eval benchmark with a score of 92.0. Multi-programming language code generation. Table 19 shifts the focus to non-Python programming tasks, evaluating Llama 3 models on the multiple benchmark. This benchmark includes translations of problems from human eval and MBPP into multiple programming languages such as C++, Java, PHP, TypeScript, TS, C, and Shell. Key findings from Table 19. There is a noticeable drop in performance when models are tasked with generating code in languages other than Python. Llama 3405B still leads in performance, but the scores are lower compared to Python benchmarks, highlighting the challenges in multi-language code generation. Multilingual benchmarks. The final section of the page introduces the multilingual capabilities of Llama 3, which supports 8 languages: English, German, French, Italian, Portuguese, Hindi, Spanish, and Thai. The evaluation is conducted using the Multilingual MMLU and Multilingual Grade School Math (MGSM) benchmarks. Multilingual MMLU. Questions, few-shot examples, and answers are translated using Google Translate, while task instructions remain in English. The evaluation is performed in a 5-shot setting, and results are averaged across the supported languages. MGSM. This benchmark assesses the model's ability to solve grade school math problems in multiple languages. The page notes that Llama 3 has not been optimized or safety-tuned for languages beyond the 8 supported ones. Developers are encouraged to fine-tune the model for additional languages, adhering to the Llama 3 community license and acceptable use policy. Summary of figures and tables. Table 18. Pass at 1 scores for code generation benchmarks, showing the performance of various models. Table 19. Performance of Llama 3 on non-Python programming tasks, indicating a drop in performance for other languages. Table 20. Referenced but not shown on this page, expected to contain results for multilingual benchmarks. Limitations and future work. The page highlights the performance drop in non-Python code generation and the need for further optimization and safety tuning for additional languages. Future work may involve enhancing the multilingual capabilities and addressing the performance gaps in multi-language code generation. In summary, this page provides a comprehensive evaluation of code generation and multilingual capabilities of various models, with Llama 3405B and GPT-4o emerging as top performers. The findings underscore the challenges in extending model capabilities across different programming languages and the importance of fine-tuning for multilingual applications. Multilingual benchmarks. Table 20 summarizes the performance of these models on 2 multilingual benchmarks: MGSM and Multilingual MMLU. MGSM, Shi et al. 2022. Results are reported in a zero-shot chain of thought (COT) setting, while Multilingual MMLU results are reported in a 5-shot setting across 7 languages. Key findings include: Llama 3405B achieves the highest score on MGSM with 91.6%, outperforming other models. On Multilingual MMLU, Llama 3405B scores 83.2%, slightly behind GPT-4o, which scores 85.5%. Llama 3 models, 70B and 8B, also show strong performance, leading among competitors in both tasks. Math and reasoning benchmarks. Table 2 presents results for math and reasoning benchmarks, including GSM-8K, Math, and GPQA. Highlights include: Llama 3.8B outperforms other models of similar sizes on GSM-8K, Math, and GPQA. Llama 370B significantly outperforms other models in its class across all benchmarks. Llama 3405B is the best in its category on GSM-8K and ARCC, and competitive on GPQA, though Claude 3.5 Sonnet leads on GPQA. Long context benchmarks. The evaluation covers tasks that require understanding and retrieving information from long texts. Key benchmarks include: Needle-in-a Haystack, Camrant, 2023, Llama 3 models achieve perfect retrieval performance, successfully retrieving 100% of needles at all document depths and context lengths. In the multi-needle variation, Llama 3 models achieve near-perfect results. Zero Scrolls, Shaham et al., 2023. This zero-shot benchmark for natural language understanding over long text shows that Llama 3405B and 70B models either match or surpass other models. Infinite Bench, Zhang et al. 2024, evaluated on N. QA and N. MC tasks. Llama 3405B outperforms all other models, with significant gains on N. QA. Tool use performance. The models are evaluated on zero-shot tool use benchmarks, including Nexus, API Bank, Gorilla API Bench, and the Berkeley Function Calling Leaderboard, BFCL. Results in Table 22 indicate Llama 3 variants perform best on Nexus. On API Bank, Llama 3.8B and 70B outperform other models in their category, with the 405B model trailing Claude 3.5 Sonnet by only 0.6%. Llama 3405B and 70B models perform competitively on BFCL, with Llama 3.8B leading in its category. Summary. This page highlights the superior performance of Llama 3 models across various benchmarks, particularly the 405B variant, which consistently ranks among the top performers. The evaluations cover a broad spectrum of tasks, demonstrating the model's versatility and robustness. The detailed results and comparisons underscore the advancements in multilingual understanding, mathematical reasoning, long-context comprehension, and tool use capabilities. The page also notes the competitive edge of Llama 3 models, particularly in larger parameter sizes, while acknowledging the strong performance of other models like GPT-4o and Claude 3.5 Sonnet in specific tasks. Long context benchmarks. The first section discusses long context benchmarks, specifically zero scrolls, quality, Casper, S-quality, N, QA, N, MC, and multineedle. The performance metrics for these benchmarks are presented in Table 21. Key metrics include exact match for quality, F1 score for Casper and infinite bench N, QA, Rouge L for S quality, and accuracy for N, MC. The multineedle benchmark tests a model's ability to retrieve specific information from long contexts, computing average recall across 10 sequence lengths up to 128K tokens. The table shows that Llama 3 models generally perform well across these benchmarks, with the 405B variant achieving the highest scores in most categories. GPT-4 also performs strongly, particularly in zero scrolls and quality. The results indicate that larger models tend to perform better in handling long-context tasks. Human evaluations. The paper also details human evaluations focused on tool use capabilities, particularly in code execution tasks. This involves collecting 2,000 user prompts related to code execution, plot generation, and file uploads from various datasets, including LLMs and Gaia. The human evaluations aim to measure more nuanced aspects of model performance, such as tone, verbosity, and cultural context understanding. Zero-shot tool use benchmarks. Table 22 presents zero-shot tool use benchmarks, reporting function calling accuracy across Nexus, API Bank, API Bench, and BFCL. The results show that Llama 3405B outperforms other models in most categories, particularly in Nexus and API Bench. However, GPT-4o excels in file upload tasks. The comparison between Llama 3405B and GPT-4o using OpenAI's Assistance API is visualized in Figure 16, highlighting Llama 3's superior performance in text-only code execution and plot generation tasks but its lag in file uploads. Prompt collection for human evaluations. The final section on this page describes the methodology for collecting high-quality prompts for human evaluations. A taxonomy was developed to capture a wide range of model capabilities, resulting in approximately 7,000 prompts across 6 individual capabilities: English, reasoning, coding, Hindi, Spanish, and Portuguese, and 3 multiturn capabilities: English, reasoning, and coding. The prompts were uniformly distributed across subcategories and difficulty levels, with 10% easy, 30% medium, and 60% hard prompts. Multiturn evaluations involved prompts with 2 to 11 turns, assessing the model's response in the final turn. Summary. In summary, this page provides a comprehensive evaluation of various language models using both automated benchmarks and human evaluations. The results underscore the importance of model size and architecture in performance, particularly in long context and tool use tasks. The detailed methodology for prompt collection ensures a robust evaluation framework, capturing a wide range of model capabilities and real-world scenarios. This section of the academic paper discusses the human evaluation results comparing the performance of the Llama 3405B model with other models like GPT-4 and Claude 3.5 Sonnet on various tasks, including code execution, multilingual prompts, and reasoning. It highlights that Llama 3405B is competitive with leading industry models, though it has mixed results depending on the specific task. Additionally, the section addresses the limitations of human evaluations due to potential biases and outlines the safety measures taken during the model's development to ensure responsible content generation. Human evaluation results. The page begins with Figure 17, which illustrates human evaluation results for the Llama 3405B model. The figure is divided into 3 sections, each comparing Llama 3's performance against different models: GPT-4, GPT-4o, and Claude 3.5 Sonnet. The results are presented with 95% confidence intervals and exclude ties, providing a robust statistical comparison. The evaluations cover various capabilities, including multilingual, long context, tool usage, and multimodal capabilities, to assess the effectiveness of safety mitigations. Assessment of uplift. The text then discusses the concept of uplift, which refers to the additional risk introduced by new technological developments compared to existing technologies like web search. This assessment is crucial for understanding the incremental risks associated with advancements in AI, particularly in sensitive areas such as cybersecurity and chemical and biological weapons. Red teaming and residual risk assessment. The methodology of red teaming is highlighted as a critical process for identifying and mitigating safety risks. This iterative approach involves continuously testing the model's capabilities to uncover and address potential vulnerabilities, thereby performing a residual risk assessment to ensure comprehensive safety measures. System-level safety. The development of system-level safety mechanisms is described, focusing on the orchestration of classifiers around the model's input and output. This approach aims to enhance safety and facilitate the customization of safety protocols for various use cases, promoting responsible deployment of generative AI. Benchmark construction. The section on benchmark construction outlines the creation of internal benchmarks inspired by the ML Commons taxonomy of hazards. Existing benchmarks like Toxigen and XS test are acknowledged, but the text emphasizes the need for new benchmarks to cover the unique capabilities of Llama 3. Human-written prompts, both adversarial and borderline, are collected to measure violation rates and false refusals. Adversarial prompts are designed to elicit harmful responses, while borderline prompts test the model's ability to handle nuanced queries without unnecessary refusals. The benchmark dataset comprises over 4,000 prompts per capability or language, including singleturn and multiturn prompts. Safety pre-training. The final section discusses the importance of incorporating safety measures throughout the model development lifecycle. During pre-training, various filters are applied to identify and exclude websites containing personally identifiable information, as detailed in Section 3.1. This proactive approach ensures that safety considerations are embedded from the earliest stages of model development. In summary, this page provides a comprehensive overview of the safety evaluation framework for the Llama 3 model, detailing human evaluation results, benchmark construction, and pre-training safety measures. The methodologies described are designed to ensure the responsible development and deployment of AI technologies, addressing both immediate and residual risks. Adversarial prompts and memorization. The page begins by presenting examples of adversarial prompts in various contexts, such as English text, multilingual text, long context, and tool use. These prompts are designed to test the model's response to potentially harmful or unethical queries. Table 23 lists these examples, highlighting the diverse scenarios in which the model's robustness is evaluated. Verbatim memorization. The subsequent section discusses the concept of verbatim memorization, where the model generates exact sequences from its training data. Table 24 provides quantitative data on the average verbatim memorization rates for different Llama models: 3.8b, 2.7b, 3.70b, 270B, and 3405B, across various NGRAM scenarios, 50 gram and 1000 gram. The results indicate that the Llama 3405B model has memorization rates of 1.13% and 3.91% for 50 gram and 1000 gram scenarios, respectively. These rates are comparable to those of Llama 2 models of equivalent size. The methodology for measuring memorization involves sampling prompts and ground truths at different frequencies using a rolling hash index of all NGRAMs in the corpus. This approach allows the researchers to construct diverse test scenarios by varying prompt length, language, and domain, and then measure the inclusion rate of ground truth sequences in the model's output. Safety fine-tuning. The final section on this page introduces the concept of safety fine-tuning, which aims to mitigate risks associated with the model's capabilities. This process involves two main components: safety training data and risk mitigation techniques. The fine-tuning methodology is adapted to address specific safety concerns, optimizing for two primary metrics. 1. Violation rate, VR. This metric captures instances where the model's response violates a predefined safety policy. 2. False refusal rate, FRR. This metric measures the frequency of the model incorrectly refusing to respond to harmless prompts. The researchers also ensure that safety improvements do not compromise the model's overall helpfulness by evaluating performance on helpfulness benchmarks. Limitations and future work. The page concludes by acknowledging the limitations of the current analysis, such as the need for metrics beyond exact match and alternative prompt search strategies. Despite these limitations, the results are deemed encouraging, suggesting that the safety fine-tuning process is effective in reducing risks without significantly impacting the model's utility. Figures and tables. Table 23 lists examples of adversarial prompts used in internal benchmarks. Table 24 shows average verbatim memorization rates for different Llama models across selected test scenarios. Connection to previous pages. This page builds upon earlier discussions of model evaluation and safety, providing detailed empirical data and methodological insights that reinforce the paper's broader objectives of enhancing model robustness and safety. In summary, page 42 provides a comprehensive analysis of adversarial prompts, verbatim memorization, and safety fine-tuning, offering valuable insights into the performance and safety of advanced language models like Llama. Model size and safety performance. The page begins by discussing the impact of model size on the balance between violation rate, VR, and false refusal rate, FRR. Figure 18 illustrates this relationship, showing that larger models, 70B, are more adept at distinguishing between adversarial and borderline contexts compared to smaller models, 8B. Consequently, smaller models require a higher proportion of safety data relative to helpfulness data to achieve comparable safety performance. Quality and design of safety training data. The quality of safety training data is emphasized as being more critical than its quantity. The paper notes that human-generated data, while valuable, can be prone to errors and inconsistencies, especially for nuanced safety policies. To mitigate this, AI-assisted annotation tools are employed to enhance the quality assurance processes. Additionally, the collection of borderline prompts, which are similar to adversarial prompts but designed to teach the model to provide helpful responses, is highlighted as a strategy to reduce FRR. Data generation and annotation techniques. Beyond human annotation, synthetic data generation is leveraged to improve the quality and coverage of training datasets. Techniques such as in-context learning, guided mutation of seed prompts, and advanced algorithms like rainbow teaming, based on map-elites, are utilized to generate diverse adversarial examples. These methods ensure a comprehensive dataset that challenges the model across multiple dimensions of diversity. Safety supervised fine-tuning. The paper outlines the process of safety supervised fine-tuning, SFT, which combines helpfulness and safety data during the model alignment stage. A borderline dataset is introduced to help the model discern subtle distinctions between safe and unsafe requests. The annotation teams meticulously craft responses to safety prompts based on established guidelines, focusing on challenging risk areas with a higher ratio of borderline examples. This strategic balance is crucial for effective safety mitigation while minimizing false refusals. Safety DPO. To reinforce safety learning, adversarial and borderline examples are incorporated into preference datasets in DPO. The paper finds that crafting response pairs to be nearly orthogonal in an embedding space is particularly effective in teaching the model to distinguish between good and bad responses. Multiple experiments are conducted to determine the optimal ratio of adversarial, borderline, and helpfulness examples, with model size influencing the learning outcomes. Different safety mixes are tailored for various model sizes to optimize the trade-off between FRR and VR. Safety results. The section concludes by indicating that the subsequent part of the paper will highlight Llama 3's general behavior along various axes and describe the results for each specific new capability, as well as the effectiveness of the safety mitigation efforts. In summary, this page provides a comprehensive overview of the methodologies and strategies employed to balance safety and helpfulness in Llama 3 models, emphasizing the importance of data quality, the role of model size, and the innovative techniques used for data generation and annotation. Figures 19 and 20 are central to this analysis. Figure 19 illustrates the VR and FRR for English and core multilingual short context benchmarks, comparing Llama 3405B with and without LG to competitor models. The languages evaluated include English, French, German, Hindi, Italian, Portuguese, Spanish, and Thai, with languages unsupported by one of the competitors marked with an X. The key takeaway from this figure is that lower VR and FRR are better, indicating a model's ability to balance safety and utility effectively. Figure 20 extends this comparison to tool usage, search, and long context benchmarks, specifically document question answering, DocQA, and many-shot learning scenarios. The VR and FRR are again the metrics of interest, with the performance for DocQA and many-shot benchmarks listed separately. Notably, the many-shot benchmark does not have a borderline dataset due to its adversarial nature, precluding the measurement of FRR. For tool usage, only Llama 3405B is compared to one competitor. The overall performance section synthesizes the findings from figures 19 and 20, emphasizing that the Llama 3405B model, particularly when coupled with LG, achieves competitive VR metrics while maintaining a low FRR. This balance is crucial as a model that always refuses responses would be maximally safe but unhelpful, whereas a model that always responds could be harmful. The internal benchmarks used to evaluate these trade-offs highlight Llama 3's ability to navigate this balance effectively. The section on multilingual safety underscores a significant finding. Safety knowledge in English does not easily transfer to other languages due to the nuances of safety policies and language-specific contexts. This highlights the challenge of developing universally safe models across multiple languages. The page concludes with a note on the limitations of the study, acknowledging that the safety benchmarks are internal to Meta and thus not reproducible externally. Consequently, the competitors evaluated against are anonymized to maintain confidentiality. In summary, this page provides a comprehensive evaluation of the Llama 3405B model's safety performance, emphasizing the importance of balancing VR and FRR, and highlighting the challenges of multilingual safety. The figures and comparative analysis offer valuable insights into the model's competitive standing in the industry. Key findings and concepts. 1. Violation and false refusal rates. Violation rate, VR, measures the frequency at which a model produces unsafe outputs. False refusal rate, FRR, measures the frequency at which a model incorrectly refuses to provide a safe response. Figure 21 illustrates the VR and FRR across different models and systems, indicating that model-level safety results in higher VR and lower FRR compared to system-level safety. Llama 3 aims to balance these metrics, unlike some competitors that are skewed towards one metric. 2. Safety data collection. The quality and distribution of safety data per language significantly impact model performance. Some languages benefit from transfer learning, while others require more language-specific data. An iterative approach is used to add adversarial and borderline data to balance FRR and VR. 3. Internal benchmarks. Figure 19, not shown on this page, compares Llama 3's VR and FRR for English and non-English languages against similar models and systems. Llama 405B with Llama Guard demonstrates superior safety compared to competing systems while maintaining competitive FRR. 4. Long context safety. Long context models are susceptible to many-shot jailbreaking attacks. To mitigate this, models are fine-tuned on SFT datasets that include examples of safe behavior amidst unsafe context. A scalable mitigation strategy is developed, significantly reducing VR without impacting FRR and helpfulness metrics. 5. Benchmarking methods. DOCQA. Document question answering tests model safety by providing long documents and related prompts to see if the model can respond safely. Many-shot. Constructs synthetic chat histories with unsafe prompt response pairs to test if the model's behavior is influenced by unsafe context. Figure 20, not shown on this page, shows that Llama 405B, with and without Llama Guard, performs better than Comp. 2 system in both DOCQA and many-shot benchmarks. Novel contributions. The introduction of a scalable mitigation strategy for long context safety, which effectively neutralizes the impact of many-shot attacks. The iterative approach to balancing FRR and VR by adding adversarial and borderline data. Limitations and future work. The need for high-quality, language-specific safety data highlights a limitation in transfer learning for certain languages. Future work may focus on further refining the balance between VR and FRR and exploring additional mitigation strategies for long context models. Figures and tables. Figure 21 displays VR and FRR across models and systems, highlighting the balance Llama 3 aims to achieve. Figure 20, referenced, shows benchmarking results for DOCQA and many-shot, indicating Llama 405B's superior performance. In summary, this page provides a comprehensive analysis of the safety performance of Llama 3 models, emphasizing the importance of balancing VR and FRR, the impact of language-specific data, and the effectiveness of mitigation strategies for long context safety. The findings underscore Llama 3's competitive edge in maintaining safety without compromising usability. Tool usage safety. The section begins by discussing the challenges associated with tool usage safety, particularly in the context of diverse tools and their integration into models. The study references Wallace et al. 2024, and focuses on the search use case, comparing Llama 405B with a competitor system, Comp. 1. The results, depicted in Figure 20, indicate that while Llama 405B is significantly safer, it has a higher rate of false refusals. Cybersecurity evaluation. The cybersecurity evaluation leverages the CyberSec-Eval benchmark framework, Bott et al. 2023-2024. Which includes tasks such as generating insecure code, malicious code, textual prompt injection, and vulnerability identification. The evaluation of Llama 3 across these tasks reveals several insights. 1. Insecure coding testing framework. Larger models like Llama 3.8b, 70b, and 405b tend to generate more insecure code but also achieve higher BLEU scores, indicating better language quality. 2. Code interpreter abuse prompt corpus. Llama 3 models, especially the 405b variant, are susceptible to executing malicious code under certain prompts, with a compliance rate of 10.4% for Llama 3405b and 3.8% for Llama 370b. 3. Text-based prompt injection benchmark. Llama 3405b is vulnerable to prompt injection attacks, with a success rate of 21.7%. Figure 22 compares these rates across different models, including GPT-4 Turbo, Gemini Pro, and Mixtral. 4. Vulnerability identification challenges. Llama 3's performance in identifying and exploiting vulnerabilities does not surpass traditional non-LLM tools in capture the flag test challenges. 5. Spear phishing benchmark. The persuasiveness and success rate of Llama 3 in spear phishing attempts are evaluated. Llama 370b and 405b are moderately persuasive, with success rates of 24% and 14%, respectively. Figure 23 illustrates the persuasiveness scores across models and objectives. 6. Attack Automation Framework. Llama 3405B's capability as an autonomous agent in ransomware attacks is assessed. The model performs well in network reconnaissance but fails in gaining initial access, executing exploits, and maintaining post-exploit access across 34 test runs. Uplift testing for cyber attacks. An uplift study measures the impact of a virtual assistant on the cyberattack success rates of novice and expert attackers. The study involves 62 internal volunteers, divided into expert and novice cohorts. The results of this study are not detailed on this page but are mentioned as part of the broader evaluation framework. Figures and tables. Figure 20 shows violation and false refusal rates for tool usage safety. Figure 22 presents text-based prompt injection success rates across various models. Figure 23 displays Judge LLM evaluated persuasiveness scores for spear phishing attempts. Limitations and future work. The page highlights several limitations, such as the higher false refusal rate of Llama 405B and its susceptibility to certain types of malicious prompts and attacks. Future work may focus on improving the model's robustness against these vulnerabilities and enhancing its performance in cybersecurity tasks. In summary, this page provides a comprehensive evaluation of Llama 3's cybersecurity capabilities, highlighting both its strengths and areas for improvement. The detailed analysis and benchmarking against other models offer valuable insights for researchers and stakeholders in the field of AI safety and cybersecurity. Prompt injection attacks. The page begins by discussing various prompt injection strategies, such as repeated token attacks, indirect references, and information overload. These techniques are used to manipulate the output of LLMs. The models evaluated include Llama 3, in various configurations, 8B, 70B, 405B, Mixtral 8x22B, Gemini Pro, and GPT-4 Turbo. A figure 22, illustrates the success rates of these prompt injection strategies across different models. The key finding is that Llama 3 models are generally more susceptible to prompt injection attacks compared to GPT-4 Turbo and Gemini Pro but less so than Mixtral models. Spear phishing persuasiveness. The next section evaluates the persuasiveness of spear phishing attempts generated by different models. The models are assessed based on their ability to craft convincing phishing messages aimed at various goals, such as malware download, data theft, and credential theft. Figure 23 presents the average persuasiveness scores, with Llama 370B acting as the judge. The results indicate that Llama 3 models generally produce more persuasive phishing attempts compared to other models. Cybersecurity challenge. The paper then describes a two-stage cybersecurity challenge designed to evaluate the effectiveness of LLMs in assisting both novice and expert users. In the first stage, participants complete a challenge using only open internet resources. In the second stage, they are provided with the Llama 3405B model. The analysis reveals that the addition of the LLM does not significantly improve the completion rates of the challenge, indicating limited utility in this context. Uplift testing for chemical and biological weapons. The final section focuses on uplift testing to assess the risk of LLMs enhancing the capabilities of actors planning chemical and biological attacks. The study involves 6 scenarios where teams generate operational plans for such attacks. Teams are divided into control, internet-only, and LL-enabled groups, with the latter having access to Llama 3 models equipped with web search, information retrieval, and code execution capabilities. Participants are categorized based on their skill levels, and the study design is validated through a preliminary study and power analysis. The operational plans are evaluated by subject matter experts, SMEs, across various metrics, including scientific accuracy and detection avoidance. A Delphi process is used to mitigate bias in evaluations. Key findings. Quantitative analysis shows no significant uplift in performance due to the use of Llama 3 models. This holds true across aggregate analyses and subgroup evaluations, e.g., different Llama 3 models or specific scenarios. The results, validated by CBRNE SMEs, suggest a low risk of LLMs significantly enhancing the capabilities for planning chemical or biological attacks. Conclusion. The page concludes by emphasizing the robustness of the study design and the comprehensive evaluation process, which collectively ensure the reliability of the findings. The results indicate that while LLMs like Llama 3 can be manipulated through prompt injection attacks, their utility in enhancing malicious activities such as spear phishing or planning chemical and biological attacks is limited. This section of the academic paper discusses the use of red teaming to identify and mitigate risks associated with the release of Llama 3 models, particularly in the context of potential misuse for biological or chemical weapon attacks. It details the methodologies and findings from adversarial testing, including specific attack strategies and their impact on model behavior, as well as the challenges posed by multilingual contexts. The goal is to continuously improve model safety through iterative testing and expert collaboration. Tool use. The text highlights various adversarial techniques that can exploit tool use in LLMs to generate harmful outputs. These techniques include unsafe tool chaining, combining multiple tools, where one tool's violating input can lead to a cascade of mixed benign and violating outputs. Forcing tool use. Using specific input strings, fragmented or encoded text to trigger potentially violating tool inputs, which can then be accessed even if the model initially refuses to perform the search. Modifying tool use parameters, altering query words, retrying, or obfuscating initial requests in multi-turn conversations to force tool use, leading to violations. Child safety risks. A dedicated team of experts conducted child safety risk assessments to evaluate the model's potential to produce outputs that could pose risks to child safety. These assessments informed necessary risk mitigations via fine-tuning. The Llama 3 model underwent in-depth sessions using objective-based methodologies to assess risks across multiple attack vectors. Collaboration with content specialists ensured that market-specific nuances were considered during red teaming exercises. System-level safety. The text emphasizes that LLMs are often integrated into broader systems rather than used in isolation. To enhance system-level safety, a new classifier, Llama Guard 3, was developed. This classifier, fine-tuned for safety classification, detects whether input prompts or output responses violate safety policies across specific harm categories. Key features of Llama Guard 3 include support for English and multilingual text, optimized for tool calls such as search tools and preventing code interpreter abuse. Quantized variants, available to reduce memory requirements. Encouragement for developers. Developers are encouraged to use these system safety components as a foundation for their own use cases. Taxonomy and training data. Llama Guard 3 is trained on 13 hazard categories from the AI safety taxonomy, including child sexual exploitation, defamation, elections, hate, and more. The training data starts with English data from Llama Guard and expands to include new capabilities like multilingual and tool use. Prompt engineering is employed to increase the number of unsafe responses in the training set, and Llama 3 is used to obtain response labels. Extensive cleaning of collected samples is performed using both human and LLM annotations, with human labels proving slightly better for borderline prompts. Results. Llama Guard 3 significantly reduces violations across capabilities, achieving a 65% reduction on average across benchmarks. The text notes that adding system safeguards and safety mitigations generally improves safety outcomes. Conclusion. This page builds upon previous discussions by detailing specific adversarial techniques, child safety risk assessments, and the development of system-level safety mechanisms. It underscores the importance of comprehensive safety measures in the deployment of LLMs and provides a robust framework for future improvements and applications. Key findings and data presentation. Table 25 is central to this page, showcasing the violation rate, VR, and false refusal rate, FRR, for Llama Guard 3 across various languages: English, French, German, Hindi, Italian, Portuguese, Spanish, and Thai. The table compares three configurations: input Llama Guard, output Llama Guard, and full Llama Guard. The VR and FRR metrics are presented as percentages relative to the base Llama 3 model. with lower VR indicating fewer model violations and higher FRR indicating more refusals of benign prompts. For instance, in English, the full Llama Guard configuration shows a 86% reduction in VR but a 102% increase in FRR, highlighting the trade-off between reducing harmful outputs and increasing false refusals. System safety and flexibility. The text emphasizes the flexibility of Llama Guard 3, which can be tailored to specific harm categories, allowing developers to balance the trade-off between VR and FRR based on their use case. Table 26, not fully detailed on this page, is mentioned as providing insights into violation reductions per category, aiding developers in making informed decisions about which categories to enable or disable. Quantization for deployment. To facilitate easier deployment, Llama Guard 3 is quantized using the int8 quantization technique, reducing its size by over 40%. Table 27, also not fully detailed on this page, demonstrates that this quantization has a negligible impact on model performance, making it a practical solution for resource-constrained environments. Prompt-based system guards. The page introduces two prompt-based filtering mechanisms, Prompt Guard and Code Shield. Prompt Guard. This is a model-based filter designed to detect prompt attacks, which are malicious input strings intended to subvert the LLM's intended behavior. It is a multi-label classifier fine-tuned from the MDBERT 3 model, 86M parameters. Prompt Guard detects two types of prompt attacks: direct jailbreaks and indirect prompt injections. The model's performance is evaluated on several datasets, including in-distribution and out-of-distribution datasets, as well as multilingual datasets. The results indicate that Prompt Guard generalizes well and performs robustly across different distributions. Code Shield. This system-level protection focuses on detecting insecure code generation before it can be used in downstream applications. It leverages the Insecure Code Detector, ICD, a static analysis library that uses a suite of tools to analyze code across 7 programming languages. This mechanism is particularly useful for developers who need to ensure the security of code generated by LLMs. Figures and future work. The text references figures 19, 20, and 21, which visually represent the trade-offs between VR and FRR, although these figures are not included on this page. The discussion suggests that future work could involve further refinement of these safety mechanisms and their application to other harm categories or languages. Conclusion. Page 50 provides a comprehensive overview of the Llama Guard 3 system's capabilities, emphasizing the balance between reducing harmful outputs and managing false refusals. It highlights the flexibility and practicality of deploying these safety mechanisms, supported by empirical data and methodological innovations. The introduction of Prompt Guard and Code Shield represents significant advancements in the field of LLM safety, offering robust tools for developers to ensure responsible AI deployment. Performance metrics. Table 26 provides a comparative analysis of the false refusal rate, FRR, and violation rate, VR, of Llama Guard 3 relative to the Llama 3 model across various safety categories. The categories include child sexual exploitation, defamation, elections, hate, indiscriminate weapons, intellectual property, nonviolent crimes, privacy, sex-related crimes, sexual content, specialized advice, suicide and self-harm, and violent crimes. The table shows 3 configurations: Input Llama Guard, Output Llama Guard, and Full Llama Guard. Key findings include: false refusal rate. The full Llama Guard configuration shows a plus 102% increase in FRR relative to Llama 3, indicating a higher rate of false refusals. Violation rate. Significant reductions in VR are observed across most categories, with full Llama Guard achieving a 100% reduction in categories like defamation, elections, intellectual property, nonviolent crimes, and sexual content. However, an increase in VR is noted for indiscriminate weapons, plus 140%, in the Input Llama Guard configuration. Table 27 examines the impact of int8 quantization on Llama Guard 3's output classification performance across different model capabilities: English, multilingual, tool use. Metrics such as precision, recall, F1 score, and false positive rate, FPR, are reported for both non-quantized and quantized models. Key observations include English capability, high precision, 0.947, and recall, 0.931, with minimal impact from quantization. Multilingual capability, slight reduction in recall, 0.805 to 0.785, due to quantization, but overall performance remains robust. Tool use capability. Quantization improves FPR from 0.176 to 0.155, indicating better performance in this category. Limitations. Section 5.4.8 discusses the limitations of the Llama Guard 3 system. Despite extensive testing, the system cannot guarantee exhaustive identification of all risks. Potential issues include harmful content generation, due to diverse training datasets, especially in non-English languages. Adversarial attacks. Skilled adversaries may find ways to jailbreak the model. Ongoing research. Continuous efforts are needed to identify and mitigate risks, and developers are encouraged to adopt responsible practices. Inference techniques. The page introduces two main techniques to enhance inference efficiency for the Llama 3405B model. 1. Pipeline parallelism. Due to the large size of the model, BF16 precision parameters do not fit into the GPU memory of a single machine with 8 NVIDIA H100 GPUs. The solution involves parallelizing model inference across 16 GPUs on 2 machines, leveraging high NVLink bandwidth within each machine. 2. FP8 quantization. The implementation of FP8 quantization has been publicly released, aiming to further optimize inference efficiency. Conclusion. This page provides a comprehensive overview of the performance, limitations, and inference techniques for the Llama Guard 3 system when applied to the Llama 3 model. The detailed tables and discussions highlight the system's strengths in reducing violation rates across various safety categories, while also acknowledging the challenges and ongoing efforts required to ensure safe and efficient model deployment. Performance metrics for Prompt Guard. The table on this page, Table 28, provides performance metrics for Prompt Guard across different types of jailbreaks: metric jailbreaks, injections, out-of-distribution jailbreaks, multilingual jailbreaks, and indirect injections. The metrics include true positive rate, TPR, false positive rate, FPR, and area under the curve, AUC. The results indicate high TPRs across all categories, with metric jailbreaks achieving the highest TPR at 99.9% and indirect injections the lowest at 71.4%. The FPRs are relatively low, with the highest being 5.3% for multilingual jailbreaks. The AUC values are close to 1.0, indicating excellent performance, particularly for injections and metric jailbreaks. Microbatching for inference optimization. Figure 24 illustrates the effect of microbatching on inference throughput and latency during the prefilling and decoding stages. The figure shows that microbatching significantly improves throughput while slightly increasing latency. The use of tensor parallelism and pipeline parallelism is discussed, with the latter being preferred across nodes due to lower bandwidth and higher latency constraints. The paper notes that while pipeline parallelism introduces efficiency concerns during training, bubbles, these are not an issue during inference. Microbatching allows for concurrent execution of microbatches, enhancing throughput despite additional synchronization points. FP8 quantization. The section on FP8 quantization describes experiments leveraging the native FP8 support of H100 GPUs for low-precision inference. The authors apply FP8 quantization to most matrix multiplications within the model, particularly in the feed-forward network layers, which constitute about 50% of the inference compute time. However, self-attention layer parameters are not quantized. Dynamic scaling factors are used to maintain accuracy, and CUDA kernels are optimized to minimize the overhead of scale calculations. The paper highlights that the Llama 3405B model is sensitive to certain types of quantization, necessitating specific adjustments. 1. No quantization is performed in the first and last transformer layers, following Zhang et al., 2021. 2. Hyperplexity tokens, such as dates, can cause large activation values, leading to high dynamic scaling factors and potential underflows, which can introduce decoding errors. Additional resources. The paper provides links to the FP8 kernels and usage examples, facilitating reproducibility and further experimentation by other researchers. Conclusion. This page builds upon previous discussions on the efficiency and performance of the prompt guard system, introducing advanced techniques like micro-batching and FP8 quantization to optimize inference. The findings underscore the importance of balancing throughput and latency and highlight the sensitivity of model performance to quantization strategies. Future work may focus on further refining these techniques and exploring their applicability to other models and tasks. The page begins by illustrating the difference between tensor-wise and row-wise FP8 quantization, as depicted in Figure 25. Row-wise quantization, which computes scaling factors across rows for parameter and activation matrices, is shown to be more granular and effective compared to tensor-wise quantization. This granularity allows for more precise adjustments, leading to better performance. A significant issue addressed is the effect of quantization errors. The authors note that while standard benchmarks often suggest that FP8 inference performs comparably to BF16 inference, these benchmarks do not fully capture the nuances of FP8 quantization. Specifically, without upper bounding the dynamic scaling factors, the model can produce corrupted responses despite strong benchmark performance. To mitigate this, the authors propose an upper bound of 1200 for the dynamic scaling factors. To better understand the impact of FP8 quantization, the authors analyzed the distribution of reward model scores for 100,000 responses produced using both FP8 and BF16. Figure 26 presents this reward score distribution, demonstrating that the FP8 quantization approach has a negligible impact on the model's responses. This finding underscores the robustness of the proposed FP8 quantization method. The page also includes an experimental evaluation of the efficiency of FP8 inference. Figure 27 illustrates the throughput-latency trade-off during the prefill and decoding stages of FP8 inference with Llama 3405B, using 4096 input tokens and 256 output tokens. The results are compared to a two-machine BF16 inference approach. The findings reveal that FP8 inference offers up to a 50% improvement in throughput during the prefill stage and a significantly better throughput latency trade-off during decoding. In summary, this page highlights the advantages of row-wise FP8 quantization over tensor-wise quantization, the importance of upper bounding dynamic scaling factors to prevent corrupted responses, and the efficiency gains achieved with FP8 inference. The figures provided support these claims, showing minimal impact on model responses and substantial improvements in throughput and latency. These insights build upon previous discussions in the paper, particularly those in Section 6.1, and pave the way for future work in optimizing quantization techniques for large-scale models. The section then transitions to vision experiments, where the authors describe their approach to integrating visual recognition capabilities into Llama 3 using a compositional methodology. This approach involves two primary stages. First, a pre-trained image encoder, Xu et al. 2023, is combined with the pre-trained language model by training cross-attention layers between them on a large dataset of image-text pairs. Alairac et al. 2022. This integration is visually represented in Figure 28. Second, temporal aggregator layers and additional video cross-attention layers are introduced to enable the model to process temporal information from videos, trained on a substantial collection of video-text pairs. The compositional approach offers several advantages. 1. Parallel development of vision and language modeling capabilities. 2. Avoidance of complexities associated with joint pre-training on visual and language data, such as tokenization issues and modality contention. 3. Assurance that text-only task performance remains unaffected by the addition of visual recognition capabilities. 4. Increased efficiency during inference by avoiding the need to pass full-resolution images through the language model's feedforward networks. The authors note that their multimodal models are still under development and not yet ready for release. Before delving into the experimental results in sections 7.6 and 7.7, the authors outline the data used for training visual recognition capabilities, the architecture of the vision components, scaling strategies for training, and pre-training and post-training methodologies. In Section 7.1, the focus shifts to the data used for training, specifically image and video data. Section 7.1.1 details the image data, which involves training the image encoder and adapter on image-text pairs. The dataset construction follows a complex data processing pipeline with four main stages. 1. Quality filtering. Non-English and low-quality captions are removed using heuristics like low alignment scores from CLIP. Radford et al. 2021. Ensuring only high-quality image-text pairs are retained. 2. Perceptual deduplication. Redundant data is removed to enhance model performance and reduce training compute, as supported by previous studies. Esser et al. 2024. Lee et al. 2021. Abbas et al. 3. Resampling. This step is implied but not detailed on this page. 4. Optical character recognition, OCR. This step is also implied but not detailed on this page. Additionally, safety mitigations are applied throughout the data processing pipeline to ensure the dataset's integrity and appropriateness. In summary, this page provides a comprehensive overview of the methodology and data processing techniques used to integrate visual recognition capabilities into Llama 3, highlighting the advantages of a compositional approach and detailing the rigorous data preparation steps involved. A significant portion of the page is dedicated to the deduplication of training data, which is essential for both efficiency and privacy. The authors employ an internal version of the state-of-the-art SSCD, self-supervised copy detection, model, as referenced by Pizzi et al. 2022, to identify and remove duplicate images. The process involves computing a 512-dimensional representation for each image using the SSCD model, followed by a nearest neighbor, NN, search across the dataset using cosine similarity. Images exceeding a certain similarity threshold are considered duplicates and are grouped using a connected components algorithm, retaining only one image text pair per group. To enhance the efficiency of this pipeline, the authors pre-cluster the data using k-means clustering and utilize FAISS, Facebook AI Similarity Search, for NN searches and clustering. The page also discusses the resampling strategy to ensure diversity in the image text pairs, drawing on methodologies from Xu et al. 2023, Mahajan et al. 2018, and Mikhailov et al. 2013. This involves constructing a vocabulary of NGRAMs from high-quality text sources, computing their frequencies, and resampling the data based on these frequencies. Specifically, image text pairs containing low-frequency NGRAMs are retained, while those with high-frequency NGRAMs are sampled probabilistically. This resampling technique enhances performance on low-frequency categories and fine-grained recognition tasks. Optical character recognition, OCR, is another critical component discussed. The authors improved their image text data by extracting text from images using a proprietary OCR pipeline and concatenating it with the image captions. This addition significantly boosts performance on tasks requiring OCR capabilities, such as document understanding. To further enhance document understanding, the authors render document pages as images and pair them with their respective text, obtained either directly from the source or via a document parsing pipeline. This method ensures that the model is well equipped to handle document-related tasks. The page concludes with a brief mention of safety considerations, emphasizing the importance of ensuring that the pre-training dataset for image recognition does not contain inappropriate content. This focus on safety underscores the author's commitment to ethical AI development. In summary, this page provides a comprehensive overview of the methodologies employed to enhance the multimodal capabilities of the Llama 3 model, including data deduplication, resampling, OCR integration, and document transcribing. Each technique is meticulously designed to improve the model's performance across various tasks, ensuring both efficiency and diversity in the training data. Data filtering and augmentation. Unsafe content filtering. The paper emphasizes the importance of filtering out unsafe content, such as child sexual abuse material, CSAM, using perceptual hashing techniques like photo DNA and proprietary classifiers. Additionally, a media risk retrieval pipeline is employed to identify and remove not safe for work (NSFW) content, including sexual and violent material. This rigorous filtering is posited to enhance the safety of the final model without compromising its utility. Face blurring. All images in the training set undergo face blurring to protect privacy, ensuring that the model does not inadvertently learn or reproduce identifiable facial features. Annealing data. An annealing dataset is created by resampling image caption pairs to a smaller volume, approximately 350 M examples, using NGRAMS, which favor richer text descriptions. This results in a higher quality data subset. The dataset is further augmented with approximately 150 M examples from 5 additional sources. 1. Visual grounding. Noun phrases in the text are linked to bounding boxes or masks in the image, specified in 2 ways. Overlaying marks on the image and inserting normalized coordinates into the text. 2. Screenshot parsing. Screenshots rendered from HTML code are used, with the model tasked to predict the code that produced specific elements, indicated via bounding boxes. 3. Question-answer pairs. Large volumes of question-answering data are included to enhance the model's ability to handle such tasks. 4. Synthetic captions. Images with synthetic captions generated by an earlier model version are included, providing more comprehensive descriptions than original captions. 5. Synthetically generated structured images. These include charts, tables, flowcharts, math equations, and textual data, accompanied by structured representations like Markdown or LaTeX notation. This data improves the model's recognition capabilities and generates question-answer pairs for fine-tuning. Video data preprocessing. For video pre-training, a large dataset of video-text pairs is curated through a multi-stage process. Text filtering. Rule-based heuristics ensure minimum text length and correct capitalization. Language identification models filter out non-English texts, and OCR detection models remove videos with excessive overlaid text. Alignment filtering. Clip-style image text and video text contrastive models ensure reasonable alignment between video and text. Low similarity pairs are filtered out using image-text similarity scores and motion score-based filtering for static or low-motion videos. Dataset characteristics. The dataset comprises videos with an average duration of 21 seconds and a median duration of 16 seconds, with over 99% of videos being under a minute. Spatial resolution varies from 320p to 4K, with over 70% having a short side greater than 720 pixels. Aspect ratios range between 1:2 and 2:1, with a median of 1:1. Model architecture. The visual recognition model consists of 3 main components. 1. Image encoder. A standard vision transformer, VIT, specifically the VIT-14 variant, trained to align images and text. 2. Image adapter. Details on this component are not provided on this page. 3. Video adapter. Details on this component are not provided on this page. Conclusion. This page outlines the comprehensive data filtering and augmentation strategies employed to ensure the safety and quality of the training data, as well as the pre-processing steps for video data. It also introduces the model architecture, focusing on the image encoder component. The methodologies described are crucial for developing a robust and reliable visual recognition model, with significant emphasis on data quality and safety. To address this, the authors employ a multi-layer feature extraction strategy, incorporating features from the 4th, 8th, 16th, 24th, and 31st layers in addition to the final layer features. Furthermore, they introduce 8 gated self-attention layers before the cross-attention layers, resulting in a total of 40 transformer blocks. This enhancement increases the image encoder's parameters to 850 million and allows it to produce a 7,680-dimensional representation for each of the 256 patches. Notably, the parameters of the image encoder are not frozen during subsequent training stages, which improves performance in domains like text recognition. The image adapter introduces cross-attention layers between the visual token representations from the image encoder and the token representations from the language model. Alairac et al. 2022. These cross-attention layers, which use generalized query attention (GQA) for efficiency, are applied after every fourth self-attention layer in the language model. For the Llama 3 model with 405 billion parameters, these cross-attention layers add approximately 100 billion parameters. The image adapter is pre-trained in 2 stages. Initial pre-training on a dataset of around 6 billion image text pairs, and an annealing phase involving 500 million images to enhance performance on high-resolution tasks. The video adapter processes up to 64 frames from a video, using the image encoder for each frame. Temporal structure is modeled through a temporal aggregator, which merges 32 consecutive frames into one, and additional video cross-attention layers. The temporal aggregator is implemented as a perceiver resampler, Yeagle et al. 2021. Lalerak et al. 2022. Pre-training uses 16 frames per video, aggregated to one frame, with the number of input frames increased to 64 during supervised fine-tuning. The video aggregator and cross-attention layers have 0.6 billion and 4.6 billion parameters for Llama 3 models with 7 billion and 70 billion parameters, respectively. In the section on model scaling, the authors discuss the integration of visual recognition components into Llama 3, which now includes self-attention layers, cross-attention layers, and a vid image encoder. For smaller models, 8 billion and 70 billion parameters, a combination of data and tensor parallelization is found to be most efficient. However, for the 405 billion parameter model, pipeline parallelism is also employed. This introduces challenges such as model heterogeneity, data heterogeneity, and numerical instabilities. Model heterogeneity arises because image tokens undergo more computation than text tokens, leading to bottlenecks in pipeline parallelism. This is mitigated by ensuring each pipeline stage contains 5 layers, 4 self-attention layers and 1 cross-attention layer, and replicating the image encoder across all pipeline stages, facilitating load balancing between image and text computations. Data heterogeneity. The research identifies a significant disparity in token counts between images and their associated text, with images averaging 2,308 tokens compared to 192 tokens for text. This discrepancy necessitates more computational resources for cross-attention layers than for self-attention layers. To mitigate this, the authors introduce sequence parallelization in the image encoder, ensuring each GPU processes an equal number of tokens. Additionally, due to the shorter average text size, a larger microbatch size of 8, compared to 1, is employed. Numerical instabilities. The integration of the image encoder into the model introduces numerical instabilities when performing gradient accumulation in BF16 precision. This instability is attributed to the compounded errors from image tokens introduced via cross-attention layers. To address this, the authors switched to FP32 precision for gradient accumulation, thereby stabilizing the numerical computations. Pre-training. Image pre-training. The model initialization leverages pre-trained text model and vision encoder weights, with the vision encoder unfrozen and the text model weights frozen. The training utilizes 6 billion image text pairs, resizing each image to fit within 4 tiles of 336 by 336 pixels. A global batch size of 16,384 and a cosine learning rate schedule with an initial rate of 10^4 and a weight decay of 0.01 are used. Despite initial learning rate determinations from small-scale experiments, adjustments were necessary during extended training to address stagnant loss values. Post-base pre-training, the image resolution is increased, and training continues on an annealing dataset with a reinitialized optimizer and a learning rate of 2 × 10^5. Video pre-training. Video pre-training builds on the image pre-trained and annealed weights. The video-specific components, including the video aggregator and cross-attention layers, are initialized randomly and trained while freezing other model parameters. The training uses similar hyperparameters to the image annealing stage, with minor learning rate adjustments. The process involves uniformly sampling 16 frames from each video, representing each frame with 4 448 by 448 pixel chunks, and using an aggregation factor of 16 to obtain one effective frame for text token cross-attention. The global batch size is 4096, with a sequence length of 190 tokens and a learning rate of 10^5. 4. Post-training. The post-training phase involves fine-tuning the model on curated multimodal conversational data to enable chat capabilities. Techniques such as direct preference optimization, DPO, and rejection sampling are employed to enhance human evaluation performance and multimodal reasoning. A quality tuning stage follows, using a small set of high-quality conversational data to further boost human evaluation while maintaining benchmark performance. Supervised fine-tuning data. Image. The supervised fine-tuning, SFT, data for image capabilities includes academic datasets. Existing academic datasets are converted to question-answer pairs using templates or LLM rewriting to enhance language quality and data diversity. Human annotations. Multimodal conversation data is collected from human annotators across various tasks and domains. Annotators are provided with images and tasked with writing conversations. To ensure diversity, large-scale datasets are clustered, and images are sampled uniformly across clusters. Additional images for specific domains are acquired by expanding a seed via nearest neighbors. This page provides a comprehensive overview of the methodologies and strategies employed to address data heterogeneity, numerical instabilities, and the detailed processes of pre-training and post-training for enhancing the model's multimodal capabilities. Human-in-the-loop annotations. The paper discusses an iterative annotation process where annotators are provided with intermediate checkpoints of existing models. This model-in-the-loop approach allows annotators to use model-generated outputs as starting points, which they can then refine. This iterative process not only increases the volume and efficiency of human annotations but also improves their quality by continuously updating the model with better-performing versions trained on the latest data. Synthetic data generation. The research explores generating synthetic multimodal data using text representations of images and a text input large language model, LLM. The core idea is to leverage the reasoning capabilities of text input LLMs to create question-answer pairs in the text domain and then replace the text with corresponding images. Examples include rendering text from question-answer datasets as images or converting table data into synthetic images of tables and charts. Additionally, captions and OCR extractions from existing images are used to generate more conversational or question-answer data related to the images. Video data annotation. For video data, the approach is similar to image data but with a focus on temporal understanding. Annotators are asked to generate questions and answers that require understanding multiple frames, thus steering them towards questions that cannot be answered based on a single frame. Supervised fine-tuning, SFT, recipe. The SFT process is described separately for images and videos. Image SFT. The process begins with a pre-trained image adapter, and the language model's weights are swapped with those of an instruction-tuned language model, which are kept frozen to maintain text-only performance. The vision encoder and image adapter weights are updated. The fine-tuning approach follows Wartzman et al. 2022. Involving a hyperparameter sweep, model ranking, and weight averaging of the top K models to achieve the final model. This method consistently yields better results and reduces sensitivity to hyperparameters. Video SFT. The video aggregator and cross-attention layers are initialized with pre-trained weights, while the image weights and LLM are initialized from their respective fine-tuning stages. Only the video parameters are fine-tuned on the video SFT data, with an increased video length to 64 frames and an aggregation factor of 32 to get 2 effective frames. The resolution of the chunks is also increased to match the image hyperparameters. Preference data for reward modeling. The paper also discusses the creation of multimodal pairwise preference datasets for reward modeling and direct preference optimization. Human annotations. Human annotated preference data involves comparisons between two different model outputs, labeled as chosen and rejected, with 7 scale ratings. The models used for generating responses are sampled from a pool of the best recent models, updated weekly. Annotators can optionally provide human edits to correct inaccuracies in chosen responses, balancing volume and quality. Synthetic data. Synthetic preference pairs are generated by using text-only LLMs to introduce deliberate errors into the supervised fine-tuning dataset. These errors create negative, rejected samples, which are paired with the chosen, original supervised fine-tuning data. This page builds upon previous discussions by detailing specific methodologies and their implementation, highlighting the iterative and synthetic data approaches to improve model performance. The limitations in future work are implied in the need for continuous updates and the balance between annotation volume and quality. Rejection sampling. This technique is utilized to generate on-policy negative samples by iteratively sampling high-quality outputs from a model. Non-selected outputs serve as negative samples, enriching the preference data. This iterative process ensures that the model is continually exposed to a diverse set of examples, improving its robustness and generalization capabilities. Reward modeling. The vision reward model is trained on top of a vision SFT, supervised fine-tuning, model and a language The vision encoder and cross-attention layers are initialized from the vision SFT model and are unfrozen during training, while the self-attention layers are initialized from the language and kept frozen. This configuration, particularly freezing the language enhances accuracy, especially for tasks requiring judgment based on language quality or knowledge. The training objective mirrors that of the language but includes a weighted regularization term on the reward logit square, averaged over the batch, to prevent score drift. Human preference annotations are used to train the vision creating pairs with clear rankings, edited greater than chosen greater than rejected. Negative responses are synthetically augmented by perturbing image-related words or phrases, ensuring the vision grounds its judgments in actual image content. Direct preference optimization, DPO. This method, akin to the language model's approach, involves further training vision adapters using preference data. To address distribution shifts during post-training, recent batches of human preference annotations are retained, while off-policy batches are discarded. Updating the reference model in an exponential moving average fashion every few steps, rather than always freezing it, enhances learning from data, leading to better human evaluation performance. The Vision DPO model consistently outperforms its SFT starting point in human evaluations across fine-tuning iterations. Rejection sampling for reasoning tasks. This technique addresses the lack of chain-of-thought explanations in most question-answer pairs. By generating multiple answers with different system prompts or temperatures and comparing them to ground truth via heuristics or an LLM judge, the model is retrained with correct answers added back into the fine-tuning data. Guardrails ensure only high-quality examples are included. Answers with a low probability of correctness are dropped, and the reward model selects the top K highest quality answers for retraining. Quality tuning, QT, a highly selective SFT dataset, curated and verified by humans or top models, is used to train DPO models, significantly improving response quality without compromising generalization. This process, termed quality tuning, leverages a dataset covering a wide range of scenarios to enhance human evaluations. In summary, the page outlines sophisticated techniques to refine model performance, emphasizing the importance of high-quality data, iterative sampling, and strategic model updates. These methodologies collectively contribute to more accurate, robust, and human-aligned AI systems. Image recognition results. The image recognition capabilities of Llama 3 are assessed using a variety of datasets that test different aspects of image understanding, including multimodal reasoning, natural image understanding, chart comprehension, and document analysis. The datasets and their specific purposes are as follows. 1. MMMU, U et al., 2024 This dataset is designed for multimodal reasoning, requiring the model to understand images and solve college-level problems across 30 different disciplines. The evaluation is conducted on a validation set comprising 900 images, with both multiple choice and open-ended questions. 2. VQAV2, Ontal et al., 2015. This dataset tests the model's ability to combine image understanding, language understanding, and common sense knowledge to answer questions about natural images. 3. AI2 diagram, Kembavi et al., 2016. This dataset evaluates the model's capability to parse scientific diagrams and answer related questions. The evaluation protocol is consistent with those used by Gemini and X.AI, with scores reported using a transparent bounding box. 4. Chart QA, Masri et al., 2022. This benchmark tests the model's ability to understand various types of charts and answer logical questions about them. 5. Text VQA, Singh et al., 2019. This dataset requires the model to read and reason about text and images, testing its OCR, optical character recognition, capabilities on natural images. 6. DOCVQA, Matthew et al., 2020. This benchmark focuses on document analysis and recognition, evaluating the model's ability to perform OCR and reason about document contents to answer questions. Table 29 summarizes the performance of the Llama 3 vision module across these benchmarks, comparing it to other models such as GPT-4v, GPT-4o, Gemini 1.5 Pro, and Claude 3.5 Sonnet. The results indicate that the Llama 3 Volts 405B model outperforms GPT-4v on all benchmarks but lags slightly behind Gemini 1.5 Pro and Claude 3.5 Sonnet. Notably, Llama 3405B excels in document understanding tasks. Video recognition results. The video recognition capabilities of Llama 3 are evaluated using the perception test, Petrowian et al., 2023, which assesses the model's ability to answer temporal reasoning questions. This dataset focuses on various skills such as memory, abstraction, physics, and semantics, and different types of reasoning including descriptive, explanatory, predictive, and counterfactual. The dataset consists of 11.6K test QA pairs, each associated with an average 23-second-long video filmed by 100 participants worldwide. The evaluation focuses on the multiple-choice question answering task, key findings and novel contributions. Performance. The Llama 3 Volts 405B model demonstrates competitive performance across a wide range of image recognition benchmarks, outperforming GPT-4v but slightly trailing behind Gemini 1.5 Pro and Claude 3.5 Sonnet. Document understanding. The model shows particular strength in document understanding tasks, indicating robust OCR capabilities. Temporal reasoning. The video recognition evaluation highlights the model's ability to handle complex temporal reasoning tasks, showcasing its versatility. Limitations and future work. The page does not explicitly discuss limitations or future work, but the comparative performance analysis suggests areas for improvement, particularly in matching or surpassing the performance of leading models like Gemini 1.5 Pro and Claude 3.5 Sonnet. In summary, this page provides a comprehensive evaluation of Llama 3's image and video recognition capabilities, highlighting its competitive performance and specific strengths in document understanding and temporal reasoning. The detailed benchmark results and comparisons offer valuable insights into the model's capabilities and areas for future enhancement. Key benchmarks and evaluation metrics. 1. Perception test. This benchmark assesses the model's ability to perform complex temporal reasoning. Llama 3 models show competitive performance, with the 70B parameter model achieving a score of 60.8, outperforming other models listed. 2. TVQA. This benchmark evaluates compositional reasoning, requiring spatio-temporal localization, visual concept recognition, and joint reasoning with subtitle-based dialogue. The Llama 3 70B model achieves a high score of 87.9 on the validation set, indicating strong performance in leveraging outside knowledge from TV shows. 3. NEXTQA. Focused on temporal and causal reasoning with open-ended questions, this benchmark uses Wu-Palmer similarity, WUPS, for evaluation. The Llama 3 models perform well, with the 70B model scoring 30.3, demonstrating effective temporal and causal reasoning capabilities. 4. ActivityNet QA. This benchmark tests the model's ability to understand long video clips, including actions, spatial and temporal relations, and counting. The Llama 3 models show strong results, with the 70B model scoring 56.3, and the 8B model scoring 52.7. Notably, the Llama 3 models process only up to 64 frames, which is 1 frame every 3 seconds for a 3-minute video. Methodology. Inference process. Frames are uniformly sampled from the full video clip and passed into the model with a short text prompt. For multiple-choice questions, the prompt instructs the model to select the correct answer from given options. For short-answer questions, the model is prompted to respond with a single word or phrase. Specific prompts are used to ensure precise answers, especially for NEXTQA, where the evaluation metric is sensitive to word choice. Zero-shot evaluation. All results are obtained in a zero-shot setting, meaning no part of the benchmarks was included in the training or fine-tuning data. This highlights the robustness and generalization capability of the Llama 3 models. Significant findings. The Llama 3 models, particularly the 70B parameter version, demonstrate strong performance across various video understanding tasks, often outperforming other models that leverage native multimodal processing from pre-training. The models excel in complex temporal reasoning and long-form activity understanding, despite processing a limited number of frames. Limitations and future work. The page does not explicitly discuss limitations or future work, but the reliance on zero-shot evaluation and the limited frame processing suggest areas for potential improvement, such as incorporating more frames or fine-tuning on specific tasks. Figures and tables. Table 30 summarizes the video understanding performance of the Llama 3 models across different benchmarks, highlighting their competitive edge and specific strengths in various tasks. In conclusion, the page provides a comprehensive evaluation of the Llama 3 model's video understanding capabilities, demonstrating their effectiveness and competitiveness in zero-shot settings across multiple benchmarks. The detailed methodology and significant findings underscore the model's strengths in temporal reasoning and long-form activity understanding. The speech generation component employs a streaming text-to-speech (TTS) system that generates speech waveforms in real time during language model decoding. This system is designed to improve latency, accuracy, and naturalness of speech synthesis by utilizing Llama 3 embeddings at inference time, without fine-tuning the language model specifically for speech generation. The data section is divided into pre-training and supervised fine-tuning datasets. The pre-training data consists of approximately 15 million hours of unlabeled speech recordings across various languages, filtered using a voice activity detection (VOD) model with a threshold above 0.7 to ensure quality. Additionally, the Presidio analyzer is employed to remove any personally identifiable information (PE) from the dataset. For supervised fine-tuning, the OSR training data includes 230,000 hours of manually transcribed speech recordings in 34 languages. The AST training data comprises 90,000 hours of translations in 2 directions, from 33 languages to English and vice versa. This dataset includes both supervised and synthetic data generated using the NLLB toolkit, which enhances model performance for low-resource languages. The speech segments in these datasets are capped at a maximum length of 60 seconds. The spoken dialogue data for fine-tuning the speech adapter is synthetically generated, although specific details on this process are not provided on this page. The languages supported by the speech interface are listed, encompassing a diverse range of languages from Arabic to Vietnamese. In summary, this page outlines the sophisticated architecture and extensive datasets used to endow Llama 3 with advanced speech capabilities. The integration of speech processing components, the use of system prompts for mode switching, and the focus on improving TTS performance are key highlights. The detailed description of the datasets underscores the model's robustness and versatility in handling multiple languages and speech-related tasks. The page builds upon previous sections by detailing the experimental setup and data, setting the stage for subsequent discussions on experimental results and performance evaluations. Speech generation. Synthetic data generation. The authors describe the generation of synthetic data using a subset of an automatic speech recognition (OSR) dataset comprising 60,000 hours of speech. Additionally, 25,000 hours of synthetic data are generated using the VoiceBox text-to-speech (TTS) system on subsets of data used to fine-tune Llama 3. Heuristics are applied to select a subset of fine-tuning data that matches the distribution of speech, focusing on short, simple prompts devoid of non-text symbols. Text normalization (TN) and prosody model (PM). The TN model is trained on a dataset of 55,000 samples covering various semiotic classes, e.g., numbers, dates, times, that require complex normalization. Each sample pairs written-form text with its normalized spoken-form counterpart, guided by handcrafted TN rules. The PM training data includes linguistic and prosodic features extracted from a 50,000-hour TTS dataset, consisting of transcripts and audios recorded by professional voice actors. Llama 3 embeddings. Llama 3 embeddings are extracted from the 16th decoder layer of the Llama 3.8b model. These embeddings are aligned with the corresponding chunks in the native input sequence for TN or PM, allowing for the training of TN and PM modules with streaming input of Llama 3 tokens and embeddings. Model architecture. Speech understanding. The speech module comprises two successive components, a speech encoder and an adapter. The output from the speech module is fed directly into the language model as token representations, facilitating direct interaction between speech and text tokens. This approach contrasts with the vision module, which uses cross-attention layers to integrate multimodal information. Speech encoder. The speech encoder is a conformer model with 1 billion parameters. It processes 80-dimensional MEL spectrogram features through a stride 4 stacking layer and a linear projection, reducing the frame length to 40 milliseconds. The encoder consists of 24 conformer layers, each with a latent dimension of 1536. Each layer includes two macronet-style feedforward networks, dimension 4096, a convolution module, kernel size 7, and a rotary attention module with 24 attention heads. Speech adapter. The speech adapter, containing approximately 100 million parameters, includes a convolution layer, kernel size 3, stride 2, a rotary transformer layer, and a linear layer. The convolution layer reduces the speech frame length to 80 milliseconds, providing more coarse-grained features to the language model. The transformer layer has a latent dimension of 3072 and a feedforward network with a dimension of 4096, further processing the speech information. The linear layer maps the output dimension to match the language model's embedding layer. Summary. This page provides a comprehensive overview of the methodologies for generating synthetic speech data and the architectural details of the speech understanding module within the Llama 3 language model. The use of conformer models and rotary attention modules highlights the advanced techniques employed to integrate speech and text seamlessly. The detailed description of the speech encoder and adapter underscores the complexity and sophistication of the model architecture, aimed at enhancing the language model's capabilities in handling speech data. Speech generation. Text normalization, TN. The text normalization, TN, module is crucial for ensuring the semantic correctness of generated speech. It contextually transforms written text into its spoken form, which is then processed by downstream components. For instance, the written text, 123, can be read as 123 or 123, depending on the context. The TN system employs a streaming LSTM-BASED sequence tagging model that predicts a sequence of handcrafted TN rules to transform the input text. This model also incorporates Llama 3 embeddings via cross-attention, leveraging the contextual information encoded in these embeddings. This setup allows for minimal text token lookahead and supports streaming input-output, enhancing the efficiency and accuracy of the text normalization process. Prosody modeling, PM. The prosody modeling, PM, module aims to enhance the naturalness and expressiveness of synthesized speech. It integrates a decoder-only transformer-based model that utilizes Llama 3 embeddings as an additional input. This integration leverages the linguistic capabilities of Llama 3, using both its textual output and intermediate embeddings at the token rate to improve the prediction of prosodic features. The PM predicts three key prosodic features: log duration of each phone, log F0, fundamental frequency, average, and log power average across the phone duration. The model architecture includes a unidirectional transformer with 6 attention heads, cross-attention layers, and dual fully connected layers with a hidden dimension of 864. A distinctive feature of the PM is its dual cross-attention mechanism, which efficiently manages varying input rates without requiring explicit alignment. Training recipe for speech understanding. Speech pre-training. The training of the speech module is conducted in 2 stages. The first stage, speech pre-training, uses in-labeled data to train a speech encoder that generalizes well across different languages and acoustic conditions. The second stage involves supervised fine-tuning, where the adapter and pre-trained encoder are integrated with the language model and trained jointly while keeping the LLM frozen. This stage uses labeled data to enhance speech understanding capabilities. Multilingual OSR and AST modeling. Multilingual automatic speech recognition, OSR, and automatic speech translation, AST, often face challenges like language confusion and interference, leading to degraded performance. A common mitigation strategy is to incorporate language identification, LID, information on both the source and target sides. However, this can reduce the model's generality and zero-shot performance. To address this, the authors designed system prompts that include LID information only for the text to be emitted, target side, and not for the speech input, source side. This approach potentially allows the model to handle code-switched speech. For OSR, the system prompt is, repeat after me in, language, and for speech translation, it is, translate the following sentence into, language. These prompts have been effective in guiding the language model to respond in the desired language during both training and inference. Speech pre-training algorithm. The self-supervised BESTRQ algorithm is used for pre-training the speech encoder. This algorithm is designed to enhance the model's ability to generalize across various languages and acoustic conditions, providing a robust foundation for subsequent supervised fine-tuning. In summary, this page outlines the sophisticated methodologies employed for speech generation and understanding, emphasizing the integration of Llama 3 embeddings and advanced neural architectures to achieve high semantic correctness, naturalness, and expressiveness in synthesized speech. The training strategies are meticulously designed to balance generality and specificity, ensuring robust performance across multiple languages and conditions. Pre-training and supervised fine-tuning. Pre-training. Masking and quantization. A mask of 32 frame length is applied to the input MEL spectrogram with a 2.5% probability. For speech utterances longer than 60 seconds, a random crop of 6K frames, equivalent to 60 seconds, is performed. Feature quantization. MEL spectrogram features are quantized by stacking 4 consecutive frames, projecting 320-dimensional vectors into a 16-dimensional space, and performing a nearest neighbor search using cosine similarity within a codebook of 8,192 vectors. 16 different codebooks are used to stabilize pre-training, with the projection matrix and codebooks randomly initialized and not updated during training. Training details. The encoder is trained for 500 case steps with a global batch size of 2048 utterances, using a multi-soft max loss applied only to masked frames for efficiency. Supervised fine-tuning. Joint optimization. The pre-trained speech encoder and a randomly initialized adapter are jointly optimized with Llama 3 during supervised fine-tuning. The language model remains unchanged. Training data and parameters. The training data includes OSR, AST, and spoken dialogue data. For Llama 3.8b, the speech model is trained for 650K updates with a global batch size of 512 utterances and an initial learning rate of 10^4. For Llama 3.70b, the model is trained for 600K updates with a global batch size of 768 utterances and an initial learning rate of 4 × 10^5. Speech generation. Real-time processing. Look-ahead mechanism. The prosody model employs a look-ahead mechanism considering a fixed number of future phones and a variable number of future tokens, crucial for low-latency speech synthesis. Dynamic alignment strategy. A dynamic alignment strategy with causal masking is used to facilitate streamability in speech synthesis. This strategy aligns with the chunking process during text normalization, ensuring variable look-ahead for Llama embeddings and fixed look-ahead for phonemes. Training details. The Llama 3 embeddings are sourced from the Llama 3.8b model, which remains frozen during the training of the prosody model. The model is trained with a batch size of 1,024 utterances, each with a maximum length of 500 phones, using the AtomW optimizer with a learning rate of 9 × 10^4 over 1 million updates, following a cosine schedule after a warm-up period of 3,000 updates. Inference. Consistency in processing. The same look-ahead mechanism and causal masking strategy are employed during inference to ensure consistency with training. The model updates input phone by phone for phone rate features and chunk by chunk for token rate features. Prosody target prediction. A delayed pattern approach is used to enhance the model's ability to capture long-range prosodic dependencies, contributing to the naturalness and expressiveness of synthesized speech. Speech understanding results. Evaluation tasks. The speech interface for Llama 3 is evaluated on 3 tasks: automatic speech recognition, ASR, speech translation, and spoken question answering. Comparison models. The performance is compared with 3 state-of-the-art models: Whisper, Seamless M4T, and Gemini. ASR performance. Evaluations are conducted on English datasets from multilingual Libre Speech, MLS, Libre Speech, Vox Populi, and a subset of the multilingual FLIR dataset. The word error rate is measured, and decoding results are post-processed using the Whisper text normalizer for consistency. Summary. This page provides a comprehensive overview of the methodologies and results related to the pre-training, fine-tuning, and evaluation of a speech processing model integrated with the Llama 3 framework. Key innovations include the use of multiple codebooks for feature quantization, a dynamic alignment strategy for speech generation, and a delayed pattern approach for prosody prediction. The evaluation demonstrates the model's competitive performance against state-of-the-art benchmarks in speech understanding tasks. Automatic speech recognition, ASR, Table 31 showcases the word error rate, WER, of Llama 3 on several ASR benchmarks, including MLS, English, Libre Speech, Test Other, Vox Populi, English, and FLIR, 34 languages. The results indicate that Llama 3 outperforms specialized speech models like Whisper and Seamless M4T across all benchmarks. Notably, Llama 3's performance on MLS English is comparable to that of Gemini, highlighting its robustness in speech recognition tasks. Speech translation. Table 32 presents the blue scores for Llama 3 on speech translation tasks using the FLIR and Kovost 2 datasets. The blue score is a metric for evaluating the quality of text which has been machine translated from one language to another. Llama 3 demonstrates superior performance in translating non-English speech into English text, outperforming Whisper and Seamless M4T. This underscores the advantages of multimodal foundation models like Llama 3 in handling complex tasks such as speech translation. Spoken question answering. The paper highlights Llama 3's capabilities in spoken question answering, particularly its ability to understand code-switched speech without prior exposure. Despite being trained only on single-turn dialogues, Llama 3 can engage in extended, coherent multi-turn dialogue sessions. Figure 30, not provided on this page, presumably illustrates examples of these multilingual and multi-turn capabilities. Safety evaluation. The safety of Llama 3's speech model is assessed using the MUD-Tox dataset, which contains multilingual audio with toxicity labels. The evaluation focuses on the percentage of added toxicity, AD, and lost toxicity, LT. Table 33, not provided on this page, shows that Llama 3 has the lowest percentage of added toxicity for English, with less than 1%, and effectively reduces toxicity in its outputs. This is compared to Gemini 1.5 Pro, which had a significant number of empty responses, possibly due to safety filters or rate limits. Speech generation results. The page briefly mentions the focus on evaluating token-wise input streaming models for speech generation tasks, specifically text normalization and prosody modeling, using Llama 3 embeddings. However, detailed results and methodologies for these evaluations are not provided on this page. Limitations and assumptions. The paper notes that for some evaluations, such as FLIR ASR for Whisper v3, data for certain languages like Malayalam were not officially reported, and averages were used instead. Additionally, for Kovost 2, only 15 out of 21 languages were evaluated. The analysis of Gemini's safety results assumed all empty responses were safe, which is a conservative approach. Conclusion. Page 67 effectively demonstrates the superior performance and versatility of Llama 3 in various speech-related tasks, highlighting its potential as a robust multimodal foundation model. The evaluations underscore its competitive edge over specialized models and its capability to handle complex, multilingual, and multi-turn interactions while maintaining safety and reducing toxicity. This section of the academic paper presents various evaluations and comparisons of the Llama 3 model, particularly focusing on its speech interface capabilities, text normalization, and prosody modeling. It includes performance metrics and human evaluation results, demonstrating that models incorporating Llama 3 embeddings generally outperform those that do not, across different contexts and tasks. The text provides an evaluation of the Llama 3 8B prosody model, highlighting its superior performance in terms of naturalness and expressiveness of synthesized speech compared to baseline models. It also outlines the development and advancements of the Llama 3 model, discussing its scaling, efficiency, architectural choices, and the trend towards open-source models, as well as its post-training alignment with human feedback. Multimodal capabilities. Images. The research highlights the integration of multimodal capabilities in Llama 3, building on a substantial body of work that trains image recognition models using large datasets of image-text pairs. Notable references include Mahajan et al. 2018, and Xiao et al. 2024a. A pivotal model in this domain is Radford et al. 2021, which introduced joint embedding of images and text via contrastive learning. Llama 3's approach synthesizes ideas from recent models, e.g., Alarak et al. 2022, Dai et al. 2023, to achieve performance comparable to state-of-the-art models like Gemini 1.0 Ultra and GPT-4 Vision, as detailed in Section 7.6. Video. The paper notes the growing support for video inputs in foundation models, citing Google, 2023, and OpenAI, 2023b. However, the literature on joint video and language modeling remains limited. Llama 3 adopts an adapter approach to align video and language representations, facilitating tasks such as video-based question answering and reasoning. This methodology is supported by studies like Lin et al. 2023, and Maas et al. 2024, with results competitive with the state-of-the-art, as discussed in Section 7.7. Speech. The integration of speech and language modeling in Llama 3 is contextualized within a broader research landscape, including models like Audio PALM, Rubinstein et al. 2023, and Viola, Wang et al. 2023b. Unlike most prior work, Llama 3 does not fine-tune the language model for speech tasks to avoid potential conflicts with non-speech tasks. The research finds that at larger model scales, strong performance can be achieved without such fine-tuning, as elaborated in Section 8.4. Conclusion. The conclusion emphasizes that the development of high-quality foundation models is still nascent, with significant improvements anticipated. The Llama 3 development process underscored the importance of high-quality data, scale, and simplicity. Complex model architectures and training recipes were explored but found to be less beneficial compared to simpler approaches. The paper also discusses the organizational strategies crucial for developing Llama 3. For instance, to prevent overfitting on common benchmarks, a separate team handled pre-training data procurement and processing. Human evaluations were conducted by a small, independent group of researchers to maintain trustworthiness. The authors share these insights to aid the research community in understanding key factors in foundation model development and to foster informed public debate. Preliminary experiments with multimodal capabilities are shared to accelerate research, even though these models are still under active development and not yet ready for release. Summary of figures and tables. While the page does not contain specific figures or tables, it references sections 7.6, 7.7, 8.4, where detailed results and comparisons can be found. Limitations and future work. The page acknowledges that the multimodal models are still under active development, indicating ongoing efforts to refine these capabilities. The organizational decisions and methodological choices discussed provide a roadmap for future improvements and research directions. In summary, this page provides a comprehensive overview of the multimodal capabilities of Llama 3, the strategic decisions underpinning its development, and the broader implications for the field of foundation models. The decision to release Llama 3 publicly is underpinned by the positive outcomes from extensive safety analyses conducted throughout the study. These analyses likely involved rigorous testing for biases, robustness, and potential misuse scenarios, ensuring that the models meet high safety standards before being made available to the public. The authors argue that such transparency is crucial for the responsible development of foundation models, which are the bedrock for more advanced AI systems, including artificial general intelligence, AGI. The page underscores the importance of public access to foundation models, suggesting that it plays a pivotal role in the responsible evolution of AI technologies. By making Llama 3 available, the authors aim to set a precedent for the industry, advocating for an open and responsible approach to AGI development. This move is expected to catalyze innovation, as researchers and developers can build upon the Llama 3 models, identify potential improvements, and address any safety concerns that may arise. The authors also express a hope that the release of Llama 3 will inspire other entities in the AI industry to adopt similar practices. This could lead to a more collaborative and transparent environment, where the collective efforts of the research community drive the development of safer and more effective AI systems. In summary, this page highlights the culmination of the research efforts with the public release of the Llama 3 language models. It emphasizes the dual goals of accelerating AI development and ensuring safety through community scrutiny. The authors advocate for transparency and responsible development, aiming to influence industry practices positively. This release is presented as a critical step towards the open and responsible advancement of AGI, setting a benchmark for future developments in the field.